for joining today's webinar. And I feel really happy that our AOGS Regional Advisory Committee, RAC, has been so active having such a wonderful event. And today's topic is air pollution, remote sensing and air pollution. And that's air, we live in one big atmosphere of the Earth, and all continuous. There is no boundary. But the air pollution or something like climate, that's more regional than global. So today, remote sensing has been so powerful tool to study such regional phenomena. And that is why our RAC has air pollution studying research group, working group. And I hope all of you enjoy today's webinar through many fantastic talks. And thank you very much again for joining.
Yeah, thank you very much, Sato-san, for the encouraging words. And I would just also want to say a few words to introduce this webinar. It started years ago by the chair of our air pollution working group, Professor Umesh Kuswester, and he's very dynamic, energetic, and working very hard. So they proposed to organize such a forum in cooperation with the Taiwan Space Union, where I am working on, and also with his university, Jawaharlal Nehru University. So it's kind of a free party cooperation. And first in February last year, we have a webinar like this. So it's we call it Bilateral India-Taiwan, but now as you can see that we have turned into a multinational activity. So we will change the name in future perhaps, but still we call it BIT for now. The BIT number 1 was held in February last year online. We have a whole day discussion like today's. And then we have a in-person meeting in Taiwan in April. And from that meeting, with a group of Indian scientists joining, the end result is that there was a white paper written by a team of experts. I think the paper had been submitted for publication, and I hope that very soon we will see that there will be the first white paper coming out of the AOGS RAC. And I think that Professor Saito will be the first one to see it, to read it. And for this year, we have this, today we have the second forum, and we are very happy, extremely happy, excited to welcome our colleagues from Nepal and from Bangladesh and Pakistan. And that is wonderful because we have been trying to reach out to them for a long time. Now they are here, and then I think that we'll work together with them in future. In this year also there will be a workshop organized in India at JNU. Maybe later on, Professor Umesh Kuswester could say a few words more about it. It will be held in September. I think it's kind of capacity building, or and in cooperation with the IRDR, if I'm correct. So there will be a strange activity triggered, promoted by the RAC, the working group pollution. I think it's very, very healthy and very good. And I look forward to today's discussion. And another thing important is that the first session will be on more on remote sensing and air pollution. And second session today, the second part will be on the aspect of public health called related to air pollution. So there's another aspect of air pollution, I think that is also coming into our view. And so I think that forum would be very, very interesting, exciting, very informative for all of us. And without ado, I will let the time to give it to Umesh. Umesh, please.
Okay, thank you very much, Professor Lin. and I welcome all the participants, especially Professor Sato, AOGS chairman. He could make it and say a few words about this forum. And first of all, I would like to thank Professor Ip also for his encouragement to develop this group, air pollution working group out of RAC, and this group has been, as Professor Ip mentioned, it's delivering its objectives. Right. So this is a slide showing the different groups, working group of activities of RAC. AOGS has one RAC Regional Advisory Committee. Chairman of that is Professor Ip. And it has got 4 working groups: low latitude ionosphere research, air pollution, coastal zone, and strong earthquake. All are active, and this activity is under this air pollution working group, which we have recently made. And this group was have given a mandate next week to organize monthly webinars on relevant topics to enhance participation from geoscientists from Asian region, Indian region, and have some participation in annual AOGS meeting to collaborate different scientists in this region. So this mandate is very well fulfilled. As you see, the first meeting next week, first meeting of this AOGS RAC Air Pollution Working Group was held in September, September 4th, 24, in fact, and where very eminent people participated, including Professor Ip, who is the activity leader of REC. So this is basically having very young and old combination of researchers on evolution. Next, please. Yeah, the second we had a webinar. That was the second activity, but webinar it was first. We had that in February last year, as Professor Ip mentioned, and this webinar basically had very good input and also the outcome from Indian and Taiwan scientists. This was the first bilateral India-Taiwan meeting, and this highlighted the issue and also the further requirement to proceed, how to proceed. That we have evolution scientists, space, remote sensing scientists, and medical doctors, they participated. And later on, next week, physical meeting was held in Taiwan, National Center University. Next week, Taiwan National Center University, Taipei, and then there a lot of dignitaries participated, including Professor Wing and former AOGS chair Chung Kung Wu, and also the Secretary General of NCU, Professor Hu Sang Lee and Dr. Stephen Lee. As you can see, the names, these are authorities of university and Taiwan who participated during that physical meeting. And also we had a team of researchers from India and Taiwan who spoke about this issue and participated. And it was a very successful meeting, followed by field laboratory visits and a lot of interaction we had. And that was the first conceiving point to have another meeting in Delhi this year. This will be going to arrive. Just show that in the end. So can you please show this next one? Next slide, please. Next, please. Hello. Yeah, this is the one participant photo. That, as you can see, major people are there. Dean, School of Medical Science, Engineering, and then other deans and professors of NCU and Indian participants. Next, please. So other activity which we had, that is white paper, we have given basically status report sort of thing in this paper. What is the situation in Indo-Pacific region, how pollution and health related issues are important, and what to do in order to have future campaigns, experiment, capacity development, exchange programs, and so on. So this it's submitted to Geoscience letter with very wide and feature objectives. So hopefully, some new program comes out of this status paper. Next, please. Then other activity as part of AOGS, RAC technical sessions we had, the book has been basically submitted and it is under print. And this book is on reactive nitrogen atmosphere biosphere interaction. This is basically outcome of a session which we conducted in AOGS 23, and where Professor Mijanur from Dhaka, Arti Bhatia from India, and this series, which is going to be basically the umbrella for this book, that is AOGS Springer Briefs in Interdisciplinary Geoscience series. This series is basically handled by Professor Yoshihara Omura, is editor-in-chief. So this maybe the wonderful book highlighting how air pollution and nitrogen efficiency issues are related and they should be tackled, and hopefully this year it will be published. Next, please. Other outcome means activity point of view, this has been that continuously our group is participating in AOGS, submitting technical sessions since 2022. Every year we are submitting some session and then conducting. It's a part of scientific activity, and also it's a kind of new collaborations as a co-chair and speakers we select from that angle. This is basically a kind of extension of AOGS activity to have a number of participant collaborators and also awareness. So this is helping AOGS also. Next, please. So this now coming to main theme related with highlighting air pollution issue. As you know, Asia-Oceania region is very huge, and it's in that Indo-Pacific region, if you see, it's very highly populated, a lot of density, so a lot of activity, energy demand, all issues, they come. Next, please. So from that angle, if you see, next, this Indo-Pacific is the largest population, and here you can see the air pollution, top environmental risk factors, they have been highlighted in this map. And next, please. I will go quickly because these are standard slides, but just because as a mandatory, I am going to highlight. Next, please. The hot spots of Indo-Pacific region, if you see, this is in Indo-Pacific, and this is Himalaya, Indo-Gangetic Plain, North China, Southeast Asia, Indonesia are one megacity, Bangkok, Delhi, like that. The major sources are fossil fuel, biomass burning, dust, shipping, emission, rapid urbanization. All you can see, these are basically contributing PM 2.5, and this, if you see the concentration of PM 2.5 in 2016, as published by some other, this is here. But when you see the difference between 2010 and 16, the difference is huge in these red spotted areas. This has to be tackled and somebody has to undertake, and part of that we can contribute something. Next, please. And the region, everybody knows that energy consumption in Indo-Pacific region is increasing from 2000 to 2023. You can see there is an increasing bar. So there is a need to tackle these emission and come out how they are transported and transformed, and how they are basically deposited, having ecological effect. So this is a part of this activity, and this is one region. And you can see the air pollution long-term trend. Next, please. Trends these are very severe, which we next week they force us to look into air pollution issue, from where pollution is coming, where it is going, where it is going to harm, what kind of ecosystem this is. So long-term trends are also very alarming. We have to take it, and the main reason is fossil fuel, as you can see next week. Next, yeah. So as you see, Professor Ripo also mentioned health issue of air pollution. This is there and standard many time. These reports come that millions of people are dying, especially children and ladies are suffering due to air pollution. So this is something taking help, multidisciplinary approach from environmental air pollution specialist and then medical doctor team. That's why we have selected in this one all type of speakers who can not only speaker, they are very core researcher in the areas. So from that angle, this is going to deliver very important objective. If you see the mortality rate in Asia, it's very high. You can see all Asian countries next week. And also, if you see the air pollution in terms of AOD values, this is very also alarming in Indo-Gangetic Plain and Southeast Asia. This it covers, what region we are focusing. Next, please. Yeah, if you see the Indian, especially the Delhi air quality, it always violates the norms what we have, national ambient air quality standard, or in terms of air quality index, is always poor. So this is already Indian government and Delhi government, so they are working and lot of money has been sanctioned. So this is already very sensitive and very active issue in India, and we want to take it further because in South Asia, Pakistan, Bangladesh, Nepal, Sri Lanka, and then extending up to further Bay of Bengal, Laos, Cambodia, and Taiwan, that we have to look into what kind of air composition is getting changed. Because when we did Indian Ocean experiment, next please, we found that a lot of haze was there over Bay of Bengal and Arabian Sea next week. And you can see this slide where Indian Ocean we did and we reported acid rain first time. Acid rain, which is basically indicating that a lot of sulfur and nitrogen oxides are there in the air, and that is damaging for ecosystem. Next, please. Yeah, slide probably. This is what I was mentioning. The acid rain pH was very low all over this deep Central Indian Ocean up to Mauritius and this whole range. So what is happening towards Taiwan over Bay of Bengal and the South China Sea, that we can look under this if we plan some experiment. Next, please. Another issue is transport of air pollution up to Himalaya, and Himalaya is getting affected. Next, please. The ecosystem of Himalaya is very sensitive, and that's why this article came out of our research. This is although in Hindi, but it says that air pollution transport from Europe and Middle East is doubled in 2.5 decades. It has been increased double. So from that angle, we have to look that also, because Himalaya is very important for all of us in Asia. Next, please. So this is slide, I will not, but these are the sectors from where air mass trajectory are found very polluted, and is already published. Next, please. Another study showed also transport. You can see the trajectory coming to Himalayan region, how these are affecting. So there is a need to develop a treaty on the lines of LRTAP, which is in Europe, to see the import and export of air pollution from one country to other, and if somebody is polluting, then the compensation is given to that other country. So this kind of calculation should be done for long range transport and transboundary air pollution. And next, yeah, This is some photographs of IICT Hyderabad, where our observatory was there. Some meeting we held on acid deposition that time. Next, please. This next. This is Maldives Observatory, which I was associated when I was South Asian coordinator for Indo-Swedish project out of that AVC. So this shows different type of instrument mounted on that observatory, and these all I used to aerosol related those I used to manage. Although there were site keepers, they used to see the local maintenance, but Nepal and Maldives and India observatory I used to look after. Next, please. This is DRS Net India. This is deposition research through student network developed by my group based on my student data for different type of pollutants. So I have given name DRS Net. Thanks to all my students for this. Then next, please. And this is some activity we undertook as part of EQRI research project, South Asian Nitrogen Hub, and this hub would deliver, for our work acid deposition in South Asia, different sites. You can see India and across South Asia, and one manuscript is communicated out of this. Next, please. So now highlighting that I had next please. Lot of measurements, site waste. What I found that remote sensing blending with my site observation basically provide very efficient analysis, spatial distribution, and other objective what we want to get is basically achieved by remote sensing. And Professor T.H. Lin from NCU is collaborating in this regard. We had a collaborative session also in AOGS 25. And what happens when we really do measurement based research? Next, please. Basically, ground-based measurements and remote sensing, they have very good clear-cut different. Next, please. This slide basically shows that if you have next slide, this slide, you can see the left side. If you have this ground-based measurement sensor based, you have very dotted. Everybody knows that. And when you club this with remote and satellite estimation, you can see now the figure, and then you get very good spatial distribution, for which this kind of data also required and expertise required that we have in our group. What is here important that based on such kind of spatial distribution, some concrete policy matters can be decided. So this is required, the importance of remote sensing clubbing with ground-based data, and especially focusing on Indo-Pacific region. Next, please. This slide, next one is this region. We want to highlight that during Indian Ocean experiment and ISRO GVP program of LC2 and ITAR, we found that Bay of Bengal is very polluted compared to Arabian Sea, and over Indian Ocean up to North Indian Ocean is polluted. So from that angle, this information we have, but what happens from this black arrow, what is shown from here to here, how this air is moving, whether this side or this side. Finally, what are, because new era of energy, what we have net 2070 for China and India, basically a major country. So we have another few years for peaking, and from that angle, emissions will affect ocean, air also, and this can be undertaken by this activity, having new campaign for this region. And in this regard, in order to discuss further what about air pollution, where and how much, we have proposed a meeting. Next, please. That is to be held in Delhi this year, September 7th, next year. Next slide. Yeah, this next slide, please. this, yeah. So this proposed meeting is on transboundary time. I'm going fast because we have to cover time and other speakers. I don't want that should be too much overlapping. The proposed meeting title is Transboundary Transport of Air Pollution. That is basically having four collaborators: Jawaharlal Nehru University, Taiwan Space Union, IR International Center for Excellence Taiwan, and Taiwan Economic and Cultural Center TECC, which is MSC in Delhi. Yesterday we had meeting with TECC, already IRDR. This meeting we are basically focusing on to invite South Asian and Southeast Asian countries participants, expert, resource person, so that the issue can be sensitized. And also we lack a lot of data in Cambodia, Laos region. Not many researchers are working independently from their country. Mostly the air pollution reports from these countries are produced by European. So we want to develop capacity for the local scientists to work on air pollution. That is also one of the mandates of this meeting. Next, please. Yeah. So to summarize, this air pollution is a very serious issue. So starting from Himalaya to Indo-Gangetic region to Bay of Bengal and up to South China Sea, that we have to look after. We have to calculate how much export-import is there of air pollution. So develop a LRTP using South Asian forum, maybe SARC, maybe, or maybe other forum. This is one of that only optional. And we need to generate some new opportunities for youth to develop some kind of new sensors or a new other project where they can have future, maybe 15-20 year future to work in the same. So some new areas of air pollution related, because as you see, when Indo-X was highlighting that the gap of energy is 25 watt per meter square, and it came out three major discoveries. One was atmospheric brown cloud, then sulfate soot, and basically brown carbon. From that angle, then further lot of thousands of scientists working on these issues, and later on now health is another issue related to all this carbon emissions, coal and petroleum related basically emissions. So from that angle, health may be another major area where air pollution, remote sensing and health can be taken together to work on that and highlight the issue for Indo-Pacific region under RAC, AOGS, whatever umbrella, but this is the best umbrella what I see covering this region. And with these words, I stop here. Thank you very much. Next. Thanks a lot. If you have any query, I will be happy to answer. Thank you very much.
Umesh, you're the chair of the first session.
Okay, so I will just further proceed.
So keep the time,
Yeah, right. So next speaker, although I have taken 5 minutes extra, but already we started late. So now I request Professor Carlo Wang, National Central University. Carlo has done a lot of work on meteorology, and he will be speaking on satellite-based assessment of long-term air pollution in Asia. Carlo, please.
Okay, so my name is Carlo. Nice to meet you, and it's my great pleasure to share my recent research work with you all guys. So this is my title. I think basically I want to share what is how the satellite can help to do the long-term trend of air pollution in Asia. So compared to previous Umi's presentation focus on India, I'm going to shift to East Asia region. So as you already know, this is very important. So you see the satellite data satellite data to monitor the whole spatial and the temporal resolution of air pollution over the big area, big domain. So then also this can be utilized to assess the impact of long-range transport on Taiwan's air quality, which is always related to our government emission control strategy and the public health. So what I'm using for this study is based on all the satellite data from the MODIS or the ARA, OMI, or the OMI data. So this is the table showing the long-term data set that I have been used in this study. And in addition to the satellite data, I also use the surface data to do some analysis, including the ground-based satellite data, ground-based air quality monitoring data from the CWA, which is the Central Weather Administration, and also the Ministry of Environment, the air quality station, as shown here. The first, I think everybody probably already know the AOD is one of the most powerful tool to demonstrate the spatial distribution of air quality. This is from about 23 years long history of average of AOD. So you will see there's several hotspots in Asia, including the India, mainland China, and especially in Beijing and Shanghai. So if we also look at the NO2, so we can see it's a more even severe hotspot in Beijing and Shanghai. And I make some study area like this bus area. I do some spatial analysis for this bus area. So, but before do the bus area analysis, I do the long-term trend analysis. I divide by 3 periods. Each one is before the 2011 with AOD map and the NO2 map. And the middle column is between the 12th to 19th in 2000. So we see the different colors showing the trend of the decreasing or increasing. So before the 2011, all the domains showing the increased trend of AOD. Okay, you see the red color, and between the 12th to 19th, you see the decreasing trend over China, but there still remain some increased trend in India. And for this NO2 is also showing the same trend for this China mega city area. You see the decreasing trend of NO2, and also but if when we compare the COVID period, you see there's some areas increased and some areas decreased. But for the China, we have you see the larger decreasing trend of NO2. So if we look at closely to the different region, as I showing you here before, there's I divided by 4 regions, and I indicates a different color for the different region. But we probably will see the higher value for mainland China region. For the warm value, like the red and the orange is a higher value, and there is a comparison. They are not showing the difference between the different years. And this is a blue line is showing the Taiwan area, the Taiwan trend. So I highlight here. So this is a monthly variation of the AOD. So you see in Taiwan, we have a significant higher AOD value during March to April. So this is due to the biomass burning from Indochina, which have been well known and well studied in our team to demonstrate the impact of biomass burning from the Indochina, particularly from Thailand or Myanmar area. So if we look at the AOD anomaly, especially in the 2000 April, so sometimes we have see a very significant anomaly for in the springtime. So due to the climate variability. So in this 2023 is La Nina year. So we see the stronger AOD transport to Taiwan. So if we look at the COVID period, because the COVID provides us a very unique time period, we can see how the NO2 emission decrease and how they impact to this region. So, but before we do NO2 data process, we do some analysis for the OMI and the TROP-OMI. Because these two satellite sensor, they provide the same NO2 value for this domain. However, there are some differences between these two products. So as you see, I use the formula as showing here, showing if the differences between these two products is higher or lower compared to the OMI's data, is 100% percentage. I show you the percentage ratio. So you see for this area, so showing the TROP-OMI is lower, and this area showing the TROP-OMI is higher. But if we see the pattern correlation, so for this area, they have a very good correlation for most of them. So even these two satellite products, they have a different performance. They have a good correlation, but we needed to be aware some area could be showing some differences. So if we apply to this study to Taiwan, we are showing the satellite and the versus surface NO2 comparison. So here showing, here is a map of Taiwan. I pick up several air quality stations around the Taiwan, and we see this is a reference station. I pick up from the station from out of around the 90 station in Taiwan. And there's several stations we consider as a background station, which is Wanli, Taidong, and Hengchun. So you can see this is the most polluted area, and this is considered as a more clean area. And I'm only showing the three stations from the Taichung, Xitun, and Xinyi, and Daliao. These three stations I pick from this map. And I showing the correlation. Okay, so the x-axis is from the EPA data, y-axis is from the NO2 satellite data. So basically, you are see the some correlation, especially in the south region, have a higher correlation. This is a seasonal variation. So basically, the satellite can present very well seasonal variation among all the stations. So if we combine all the stations, so you can see this is the TROP-OMI monthly variation. This is the OMI variation. This is EPA from the surface measurement. So they are kind of in good agreement to each other. However, the value is a little bit different. So when we have this, and then if we look at the lockdown area, lockdown period from in 2020 in March. So we see the Shanghai is a lockdown period in this week. Before, you see the NO2 is quite high before the lockdown, and after lockdown, the NO2 is showing the significant decrease until to the unlockdown week. And then we do the estimation for how much effect for the lockdown NO2 emission. So we compare the satellite TROP-OMI data in different years. This is from the Shanghai. We retrieve from the Shanghai area. So we see during the lockdown period, we see the red line is significantly decreased compared to previous years, can reduce up to the 30% compared to the original value. So this is some percentage of comparison. So that means when during the lockdown period we have a lower NO2. So and how that affected to Taiwan, we also do the same thing to our Wanli air quality data for PM 2.5. We also showing during the lockdown period that our PM 2.5 in Taiwan, the north tip of Taiwan, also showing a lower value, is a decrease up to the 30%, which is consistent with the previous study for this for Shanghai, and this is also 30%. So which is means air pollution from the Shanghai and the northern Taiwan is linked to each other. So this is correlated. So then, how can we do the more systematic analysis for the long-term transport of local air pollution and compared to the long-range transport, especially during the winter monsoon season? So we have a method. I just skip this slide. So I separate the different event, which is a long-range transport event or long-range ordinary event, and this is a pure local air pollution event. So, and you can see that during the different category, you have a see different pattern, and also affected to the Taiwan air quality. In Taiwan, the NO2 distribution many in northern, central, and south Taiwan, and the most severe air pollution in southern Taiwan. You are showing here, and this during the event you have see not only the transport of air pollution from the outside to Taiwan, also the local air pollution also very significant, very important. But compared to the pure local transport, you are not see much transport from the outside, but you see those hotspots still visible in this map. So that means when a very severe long-range transport event, the increase of NO2 air pollution will up to the 40% compared to the long-range transport ordinary case. So this is some study. I do some separation for the long-range transport and the local pollution PM 2.5. Actually, if you see this blue line is local PM 2.5, they could be kept in a very stable, but when we have a sharp decrease of long-range transport, that we can reduce our air pollution in Taiwan. However, we have some limitation for keep to this is a value 4.5. So this is for government strategy planning. So if we want to control our air pollution in the very low value, but we probably cannot reach to this value. Okay. So in the last part, I probably want just skip this because this is more related to more detail of the population weighted PM 2.5 concentration. So we have some results based on the because the previous study used a satellite to estimate the local the surface PM 2.5, but I think this value is much higher than what we expect. So we do reanalyze this data, and we showing the value is close to what I see is 70.7 microgram per cubic meter. And this is more detail if we consider the population weighted exposure, so we can down to the county scale. So this will be provide more useful information for our health assessments. So this is all my presentation. Thank you.
Thank you very much, Professor Carlo. Now we have next presentation by Professor T.H. Lin, who is Director of Remote Sensing Center in NCU, Taiwan. He will be speaking on the spectral proposal of MAPS onboard foremost 8D for air pollution monitoring. He has done wonderful work on this, and now I request Professor TH to speak. Professor.
Okay, thank you for Professor Umesh, and good day, everybody. So here I will. Okay, so I will show you the proposal. Actually, cooperate with Taiwan Space Agency, in short, TASA. in Taiwan. So I will start from the background. Actually, for the air pollutant or air pollution, actually the issues could be climate change or public health. So I would like to use this slide to show the issues highly related to the air pollution. So first of all, the issue related to the climate or weather changes. So as we all know, no matter nature or man-made emission, so after interaction with the material suspended in the air, no matter in physical format or chemical format, the particle could be grossed up. So that as you can see, here is the coarse particle, and the coarse particle may affect the incoming solar radiance, a kind of Earth radiation budget, so that the climate or weather could be affected. And the second one, as we all know, that's the public health. So especially the ultra fine particle could be easily come into human body. So the effect part could be the brain and the breast system as well as lung system. So actually, no matter climate change or the public health, actually the component of the suspended particle is very significant. For example, if we talking about the climate radiative forcing, so not only the greenhouses, but also the suspended particle, just like sulfate, black carbon, and the dust, and so on, do have different impact on that. So that how to provide this kind of information for more detailed assessment actually is very important. And here just show you some result after analyze associated with satellite observation during past 2 decades. In this study, associates with the report from WHO. So actually, the air pollution is a kind of silent killer. So the global population do about 9 million people deaths caused by the air pollution. The major cause could be include the brain system, the breast system, and the lung cancer, and so on. So this kind of the impact actually do highly related to the component because different component could cause of the different result. Here is the spatial resolution of the deaths caused by the air pollution. So if you compare with the satellite observation in annual mean PM 2.5 concentration, you may really understand the issue actually. So the detailed analysis could be for the mortality risk analysis for each different component. For example, anthropogenic pollutant here indicates the sulfate particle, and biomass. The major component could be the brown carbon and the dust. So the result just show us the different component actually equipped with different effect for different area actually. So the observation actually is very important, and no matter for the global scale or the regional scale. So satellite observation could be the best choice. However, the best the satellite observation just can provide us the aerosol optical depth in total column of the atmosphere, so that more procedure more advanced technology should be applied. So here just show you the pretty high spatial resolution in Asia region from Himawari 8 observation. So as you can see in Asia, actually the situation of air pollution is extreme severe actually. So including the Indochina, India, and the mainland China actually. So here just try to give you some fundamental concept. Just like what I mentioned from the satellite remote sensing, the general parameter or general information is the total column aerosol optical depth coming from the transmittance of incoming solar radiance. And this kind of information actually including not only concentration but also type or component associated with the vertical distribution. So when you use the satellite observation to combine with the in situ measurement on the surface, so you had better to consider about the vertical distribution actually. Okay, so for the air pollution, especially, we would like to provide more detailed information. For example, the component identification. Taiwan Space Agency, TASA, actually will focus on the air pollution, which can provide the more detail. The mission include two parts. The first one is the sensor development by themselves, and the other one is could be the applications. So in order to provide the type component, so that the aerosol optical depth retrieval algorithm could be focused on the deep blue approach. So here is the deep blue approach. So the deep blue approach may so-called the deep blue actually try to use the higher sensitivity of the deep shorter wavelengths of blue light to identify the suspended particle associated with the red band or short wave IR spectral band. Then the output, not only the aerosol optical depth, but also the single scattering albedo can be provided, which can help us to identify the type of components for the suspended particle. So here is the scheme currently proposed by the NASA, TASA, TASA. So the sensor is scheduled try to onboard the Formoset 8 number 4 ABCD. So AD means number 4 of Formoset 8, which potentially launched in the Q4, last quarter of 2028. So on the right-hand side could be the scheme of the sensor, a kind of the optical system of the sensor, including the visible spectral band as well as the short wave IR spectral band. So the information actually is provided by the TASA. Okay, so here is the spectral comparison between the main payload and secondary. Here is the main payload, which can provide a very high spatial resolution, for example, 1 meter or 2 meters. And for our proposed sensor for the air pollution monitoring, of course, in order to cover more swaths so that the spatial resolution could be not that better. Currently is about 100 or 200 in spatial resolution, actually. So once we can observe or collect this kind of observation from satellite, then the challenge of remote sensing could be presented. So the first of all, you need try to identify the aerosol type or component. So currently, we do have some preliminary result in identify or separate the dust particle, the bright carbon, and the sulfate. And actually, if you focus on the surface layer information, you had better to provide the aerosol profile as well. Once you can provide the aerosol profile, then three-dimensional distribution of suspended particle could be provided as well. So that after this kind of procedure, then it is pretty straightforward to combine the PM2.5 concentration and the fraction of each component in aerosol optical depth for more accurate concentration calculation. So I don't want to go more detail for this part. I would like just give you some concept. For the aerosol partitioning, we actually based on the in situ measurement from different surface observation. So here is the table after data collection. So for the physical parameter, in terms of the identification, we would focus two parameters. The first one could be the particle size. The second one could be the single scattering albedo, or you can think the parameter in absorption or scattering characteristic. So from the in situ measurement, actually, we can try to provide this kind of information directly. But for the satellite observation, actually, especially the single scattering albedo is usually cannot provide it. So once we can identify the aerosol component associated with the particle size and the single scattering albedo, and in terms of the observation on the top of satellite level with different spectral band, then it is pretty straightforward for us to identify or to partition the major component of the observation, actually. So from satellite observation, then we try to have the spectral aerosol optical depths. And according to the spectral aerosol optical depth, we can estimate the particle size in optical as well as the absorption or scattering capability in optical. Then apply the result into the kind of pre-construct data base, a kind of lookup table, then we will be able to have this kind of detail in component, actually. So associated with the other observation, then you will be able to identify the radiative forcing for each type for each type. And for the vertical distribution, actually, according to the in situ measurement from micropulse data, so we try to apply the normal distribution to fit the or mapping the vertical distribution of suspended particle. And here is the result in comparison with the in situ measurement. So the result seems not bad and also available for us. So that combined with these two procedures, then once we have the satellite observation after aerosol optical retrieval, then associated with the boundary layer high, we can have the vertical distribution and the surface extinction associated with the type identification. Then we'll be able to convert to the PM 2.5 concentration. And here is the comparison from the approach retrieval with the in situ measurement. The result seems pretty consistent. So the short remark could be associated with the sensor development and the deep blue approach or the aerosol partitioning approach. Then we may provide the three-dimensional of the suspended particle information actually. So once we can have this kind of information, actually, no matter radiative forcing or early warming of the environmental exposure could be provided. Okay, so it is a pretty brief presentation. So hope you can have something. So that's all for my presentation. Thank you.
Thank you very much, Professor TH, for timely completion. And these are very important publications you can note down from Professor TH. Now we have next speaker, Professor Muhammad Fatim Khokar. He is prominent environmental scientist from National University of Sciences and Technology, Islamabad, Pakistan. He has worked on climate change, atmospheric research, air pollution, and he will be talking about breathing in smoke, challenging for health and environment. Professor Khokar, please.
Thank you. Sorry for the inconvenience. First I would like to thank you all for attending this and inviting me to talk on an important issue, particularly breathing in the smoke, challenges for health and environment, a roadmap to solutions. Especially, I would like to talk in the context of Indo-Gangetic plains because it's more pervasive issues in the region. This work was carried out in a collaborative manner with the Duke universities and some other South Asian universities. Okay, recently air pollution has emerged as a major challenge across the South Asian states. And if you look at when we talk about Indo-Gangetic plains, then and especially in the context of particulate matter pollutions, so all the South Asian states are having levels well beyond the interim targets issued by are set by the WHO limits. For instance, here, interim target 1 is 35 micrograms per meter cube in annual average, but the atmospheric air quality guidelines are around 10 micrograms per meter cube. So, if you look at the population that is in those countries like in Bangladesh, Pakistan, India, and China, most of the population is actually living beyond these interim targets. The issue has become so pervasive that it has been termed as the fifth season in the country by recent publications, especially because it has a huge disruption in the socioeconomic circles and also causing huge health toll and attributing 32% of world's mortality from exposure to particulate matter pollution. Globally, 99% of the world population lives in the places where air quality exceeds the annual WHO guidelines. So, and the issue that is not actually going to end, it's increasing every year because of not adequate measures have been taken on board. So if you look at this, so these are the recent report from IQ Air. The baseline 2018 to 2024 data sets, annual averages of PM 2.5 concentrations. So most of the South Asian countries and the top 10 countries most polluted one, especially Bangladesh and Pakistan ranked second and third place. So if you look around these over the last 5 years, 2018 to 2024, so the conditions especially in Pakistan, this is quite stagnant. So there's no change, no improvement in the annual average of PM 2.5, and they are all the time hazardous levels. Okay, if you look at the different cities across the Pakistan, for instance, Islamabad, Faisalabad, Karachi, Lahore, Peshawar, and Rawalpindi. This is like the annual cycle. So none of the month is actually having healthy PM 2.5 levels across the year. Similar for the rest of years. And if you look at the winter months, our post-monsoon months, here like October onward, so all the cities are experiencing the hazardous level of PM 2.5 levels. So, and as a result, this is the recent report from United Nations Environment Program that is like the health toll that is attributed to PM 2.5 concentrations. And if you look at this, it's not just the respiratory infections, rather it has more impacts in mainstream chronic diseases that are now attributed to the PM 2.5 levels. For instance, here 25% the chronic obstructive pulmonary diseases, 20% stroke, 19% low respiratory infections, ischemic heart disease, 18%, and type 2 diabetes and neonatal disorders are also quite alarming rate. So it's not just the health, but it is also causing the mortality, as I mentioned before. Almost 32% mortality rate is attributed to the outdoor PM 2.5 concentrations. So if you look at this, the South Asian potential gain in life expectancy across the region, so especially I would like to mention here that the Indo-Gangetic plains, they have quite huge potential. If we could improve the PM 2.5 levels, we can have a huge gain in life expectancy up to more than 6 years in certain region of IGP. I listed here the challenges what we are facing here in Pakistan with respect to air pollution management, and I'm pretty sure that most of the challenges are quite common in these countries, with some exceptions. So, foremost challenge in Pakistan for air pollution management is lack of proper air quality monitoring network. So we have very few stations only in the major cities which are functioning, and so therefore we don't have sufficient data, and in order to have a scientific evidence-based policy formulation and implications. So another biggest challenge is that the data sharing culture is not very common here in this region as well. Lack of institutional capacity at at the regulator level and the policy making institute, it's not there. And then lack of policy feedback mechanism, because in the absence of having a proper air quality monitoring network, so your policies are actually without any feedback, whether they have been effective or ineffective, and if it's effective or ineffective, so in which quantity it was ineffective or effective. Another issue is transboundary air pollution that has exacerbated the issues manifolds, and also requires regional collaboration to address this issue. So lack of coordination between industry, public, and all other stakeholders is very important. And above all, technological and financial constraints make the job more difficult, and to manage the ever-increasing air pollution issues in Pakistan. Above all, if I sum up in one line, so the approach is reactive rather than proactive. So that's why air pollution levels are not reducing, rather they are stagnant or are increasing slightly over the years. So as I mentioned before, I would like to put some details on this lack of proper air quality monitoring. Recently, there have been some advancement, as the Punjab government has installed few air quality monitoring stations, but still countrywide there are very few. And if you talk about the policies regarding air pollution, so they are in place, but how effective they are, it's difficult to say. And the technological and financial constraints, because a conventional air quality monitoring cost is quite high, and along with its operation and maintenance costs. So that's another challenge, that the Pakistan remains country with worst air quality condition and scarce monitoring facilities. Okay, as I mentioned before, lack of policy feedback mechanism, lack of institutional capacity. So the biggest challenge is that most of the stakeholders are working in isolation. Their linkage among themselves is not there. They don't share evidences and data at appropriate levels. Therefore, our issues remain still unaddressed. So what could be the way forward in order to all these four challenges to address? I propose a hybrid approach, keeping in view the technical and financial constraints. So hybrid monitoring network, which is supported by the satellite observations for qualitative assessment and hotspot identification, and a constellation of conventional air quality monitoring systems deployed at strategic location, which are surrounded by low-cost sensors, and then for data analytics was supported by machine learning algos. We can actually have user feedback and through dashboards. So this is like an all-inclusive approach by taking on board all the stakeholders, and it can help, and it's cheaper, by the way, and also equally effective as well. When we talk about the low-cost sensors, then there are certain myths about the accuracy and the lifetime of the low-cost sensors and the multitude of data set they are producing every instant. So we try to debunk all these myths. So as a part of this project, along with Duke University, so the accuracy, what we actually established the first low-cost sensor network in Pakistan since 2021 onward, and it's still going on. So the accuracy of low-cost sensor is more than 90%. We validated against the BAM, the conventional air quality monitoring, PM2.5 monitoring instrument. And so we develop a dashboard that can facilitate for data handling and quick decision making. We have a rigorous validation and calibration routines, and the lifetime of low-cost sensors. With the sum of sensors we installed back in 2021, so they are working very well. So, but we extensively do the calibration and maintenance on 6 month to 1 year basis. It depends on the need. So, but how still there's a long way to go about the acceptability of PM2.5 as a reference monitors, especially in the legislative circles and the regulatory authorities. So we're still working on this, but there is a huge awareness about the accuracy and effectiveness of local sensors in Pakistan nowadays. Sorry. If you look at this here, we put a co-located low-cost sensor against the BAM in Pakistan for a couple of months, and you see there is a huge agreement between both the low-cost sensor and the BAM, and the correlation is even more than 90%. So it's cost-effective and can be a good alternative. So this is just a snapshot of air quality dashboard that we have generated here, and we're using this, and we can have a quick look at the data up to last 3 months, and we can download the data for the longer time period as well. Here we have introduced another next generation air quality data analytics tool, which especially we designed it to keep in mind the policy making, because they are non-technical person most of the time, and they don't have much intention or desire to work on data analyzing. So it's kind of ready-made, tailor-made solution for them to just a few clicks, and then they will get outcome like this, having calendar plots, weekly averages, running averages, daily averages, weekly cycle kind of things that they can have an effective and smart approach to address the issue. This is another outlook. So on the basis of our recently established network, we can have a quick look and we can have a ranking which city is actually the most polluted one, the number of days exceeding the WHO limits, number of days exceeding Park NEQs. So if you look at the Faisalabad has been the most polluted one with 330 days out of 365 days, more than WHO guideline. So similarly, we can rank and through for other time period as well. Data scarcity and data sharing is another challenge. As I mentioned before, all the stakeholders are working in silos. They're reluctant to share because of lack of technical capacity and lack of coordination among the stakeholders. So there is a huge inter and intra-department coordination deficiency and trust deficit. So therefore, the feedback mechanism is not active. And another biggest challenge is actually the transboundary air pollution. If you look at here, we try to utilize modest satellite data, aeronet surface data, then back trajectory analysis, fire activities for year 2026 for the first 7 days of November, when we have the extensive smog episodes in Lahore, city of Lahore. So we have a clear evidence that during that time of the year, most of the air pollution load is coming from agriculture fires in the neighboring region as well. So lack of awareness among all stakeholders, a broken nexus among the stakeholders, no data sharing, no information sharing, no access to the data. That makes less awareness, and particularly the people does not know what's going on, what kind of measure the government is taking, and whether they have been effective. So the social pressure is not there actually. This is another assessment which gave us like trajectory analysis at the city of Lahore, which kind of trajectory clusters are actually reaching to this region. And similar study was published by some other Anal et al. Like in 2022. So this is like this IGP activities, agriculture fire activities are actually impacting the air pollution level in different areas. Rick, Breaking South Asian smog episodes. So I strongly believe this could be a challenge, but at the same time, it offers various opportunities for regional cooperation, and it has huge potential for regional coordination. But it could be a regional threat as well, because we live in a region with geopolitical differences. So we recently published a paper along with the community from South Asian countries that countries of Indo-Gangetic Plains must unite against air pollution. So this is the only way out. Way forward for Pakistan recommendations. We devised a framework that is all inclusive and that should encompass the monitoring, regulation, management, capacity building, and awareness. I put some details here, what it could be. For instance, for monitoring, we should go for hybrid air quality monitoring approach with 90% local sensor plus 10% reference monitoring, supported by satellite-based and machine learning algorithms and tools for data analytics as well. Similarly, to establish a very effective and strong feedback loop mechanism to identify policy gap and intervention need. Effective monitoring will lead to quick decision and smart measures. So this is a conceptual diagram for this advisory system for critical air pollution events. So it has 5 pillars, which are capacity building, impact assessment, stakeholders engagement, policy actions, and citizen engagement, or citizen side. So overall, this is a two-way channel. So the feedback information comes from either way. Some other solutions which we have designed here for both indoor and outdoor and industrial emissions. CO2 bin for indoor spaces. It acts as an air purifier and CO2 sequestration units as well. It's not just capturing CO2, rather it's utilizing CO2 for other industrial application as well. CO2 arrestor for vehicular emissions, carbon sequestration tower for direct air capture. We have devised a catalytic converter for motorbikes, especially two-stroke engines. Then we designed a Nest do-it-yourself air purifier, which is quite cheaper, and everybody can do it at home. SQL, we are working on this for industrial emission capturing. Similarly, we devise a calibration chamber, which is dedicated for low-cost sensors validation and calibration purposes. We are working now the C2M reactor to convert CO2 into methanol and methane into methanol. A few key takes away. So Pakistan has also sought regional cooperation across borders to curtail this issue. Unfortunately, no positive development has been there so far. Despite the strong effort made by Pakistan, this issue has yet to be properly resolved. The results of the satellite and ground-based observations have made it clear that transport emissions, especially during post-monsoon season, plays a major role in developing and that urge to develop a sustainable solution. So keeping in view the holistic picture of deteriorating air quality conditions in Pakistan and neighboring region, it is recommended that there is a strong need to share the responsibility, especially during the post-monsoon season, by the neighbors, and share the knowledge and good practice during the rest of the year for a better future across the region. Winter smog is a recurring issue in the IGP region. Pakistan or any country alone cannot resolve the smog issue. Rather, it requires a collaborative and rigorous effort. Thank you very much.
Thank you very much, Professor Khokar, for this wonderful talk. You have some questions in chat box. Please attend that, because I'm not raising here because of lack of time issue.
Okay.
Now next, you can answer there. Thank you very much. Now, our next speaker is Dr. Kundan Lal Shrestha from Kathmandu University, Nepal. He will be talking about model and satellite-based insight into air pollution dynamics in the complex terrain of Nepal. Professor Shrestha is a modeler, air quality modeler, and a very close colleague of mine in different networks. is very renowned, known, and also he is a JSPS postdoctoral fellow in Japan. Dr. Shrestha, now floor is yours. You have 20 minutes. Try to finish within that, and let us hope modeling contribution for air quality.
Yeah, thank you. So first of all, I'd like to thank Professor Kultresha for giving me this opportunity and linking with this wonderful group. So I'd like to present my presentation here. So right now I'm at Kathmandu University in Nepal. So I'd first introduce Nepal and its terrain. So why air pollution is a big challenge in our country. So for that, you have to look into its geography. So it's a landlocked Himalayan nation between China and India, and you can see that it has a lot of peaks on the northern side. So we broadly categorize, even though it's like 800 kilometers by around 200 kilometers width. So within that 200 kilometers also, you have a very large variation in the elevation going from a very low area of, we call it Tarai, to the high mountains. So we normally differentiate between three regions: Tarai, hills, and mountains. And the topography is one of the very important aspects when we talk about air pollution dispersion. So in demographics, we have around 30 million population, and one of the major hotspots is the Kathmandu Valley, which I have highlighted here. So it has around 3 million population. The economy is heavily reliant on tourism and agriculture. So because of the very sensitive, you could say, tourism sector, the air pollution is one of the factors that will determine the growth of tourism in Nepal. So urbanization is another big challenge for us, and in fact, the Kathmandu Valley, which contains our capital, is one of the most rapidly urbanizing cities in the world. So it is creating a big challenge for us because the air pollution is also getting concentrated in this region. And of course, the climate and biodiversity, when we talk, so one of the key receptors are the glaciers in the high mountains. So another big challenge for us. So there are a lot of studies going on about the impact of air pollution on these glaciers. To briefly summarize the air pollution status in Nepal. So air pollution has surpassed, you could say, the water pollution impacts. Just like here, you can see it has mortality impact quite significant. Then the pollution levels, nearly 89% of the population lives where PM2.5 levels exceed WHO interim target. So we can see here that WHO standard is, you could say, missed in much of the region where the people live. So that is one of the problem in our country. Regarding the source contribution, so just like the residential cooking, heating industry, of course, has quite less compared to other countries. Then the transportation, then the agriculture, as well as these are the local sources, as well as these we have transboundary sources as well. So the economic burden is quite high. So nearly 6% of our GDP is lost due to this air pollution. And the transboundary effect also is one of the problem because of the, you could say, high pollution region in the Indo-Gangetic Plain. So we call it Indo-Gangetic Plain and Himalayan foothill. So one of the key aspect will be in Kathmandu Valley. So because most of the urbanization is happening in this region, so the topography is again aggravating this air pollution trap, we call it, right? So because it's a bowl-shaped valley, so that's why there is temperature inversion, and especially in the winter season, it's a big challenge for us. So the sources of pollution as well as the topography plays a big role here. So there are a lot of valley hotspots we can think about. So that is why even the municipality has also started its own air pollution strategies at the, you could say, local level. So there is government level, then the local municipality level. So both are doing their work right now. So you can see that now in winter season, it is getting very high, just like in February 8, you can see the AQI is going quite high, and its Kathmandu Valley's ranking is 7th most polluted city. But there are some governmental decisions, just like if the AQI goes beyond 300, so we have some kind of emergency protocols right now. Now, as I said, one of the three key factors is the monsoon-dominated climate in our region. So you can see that during the monsoon, the air pollution problem gets very reduced compared to the dry winter season, which I will show later on. And the temperature inversion plays a big role as well. So just to give you an idea, so about the PM 2.5. So PM 2.5 is the most critical air pollutant here. And the annual average you can see in Kathmandu Valley, it's approximately 37 micrograms per cubic meter. And in the Tarai, the lowland area, we have around 35 micrograms. But that is also only the average and the hotspots as well. So these are quite high compared to the WHO guidelines. And in the regional context, this IGP-HF region kind of acts as a quite big airshed region. So the World Bank also has given some, you could say, guidelines, or you could say some studies where I was also involved. So we call it 35 by 35 vision. So by 2035, we want to achieve the WHO target 1. So there are lots of air quality monitoring stations you can see, but they are mostly in the Tarai region and very few in the Himalayan region. So mostly these are the EDM sensors, but there are some studies with low-cost sensors as well. So you can see the trend here. So this is the ground station data. You can see the clear trend of very high concentration of PM 2.5 in the you could say this winter season or the dry season, and in the monsoon you can see very markedly low concentration. So this is another diagram showing the same feature here, and you can see that in the southern Tarai region it has a lot of high concentration of PM 2.5, and there is of course the very high concentration in the Kathmandu Valley as well. So you could say our main focus is on, one is the urbanization. We see urban heat island effects. Then other sources like the road dust, vehicles, then comes the brick kilns, and visibility, since our tourism is impacted by this. So visibility is another factor. Then, of course, the transboundary transport due to, let's say, wildfire, as well as local and regional open burning. So we are using remote sensing as well as portable sensors and doing modeling as well at different scale. So you can see here that in Kathmandu, most of the sources are the local sources, as you see here in the blue color, and in the Tarai region, so the most of the contribution is the transboundary effect, you can see in the gray color. So chemical transport modeling we do especially with WAFCAM at different scales, as you can see, from South Asian region to the country scale and the Kathmandu Valley scale. Then we have seen a lot of impact of urban heat island. So we can even see its impact on the urban pollution island. As you can see here, this is the Kathmandu Valley. You can see the urban pollution island as well. Then some key examples I'll show you here. So like the impact of wildfire, let's say. So in the dry season, you can see a lot of fire events here, as we can see here. And this is, you can see the wildfire season here, very big peaks here, you can see. So using WAF-Chem model, using the typical chemistry options here. So we have found out these contribution of the wildfire. As you can see, this is the percentage contribution here in December 2020. So you can see a lot of hotspots, especially. So this is, of course, only for 1 month. Even then, you can see quite a good amount of contribution in nearly all the criteria pollutants. So this also is the same figure, but using Sentinel or the Topomi dataset. So similarly for carbon monoxide, then we have validated with the ground station data. So here you can see the peak in the same season. So again, to validate our model, so we have, because the ground data is quite scarce and there's a challenge of missing data. So what we did was try to use the remote sensing data to validate our model. Just like here, we have used for nitrogen dioxide as well as carbon monoxide. So basically, we have used the averaging kernel data, which indicates how the sensitive it is towards the altitudes. Then we have vertically integrated these data. So you can see one of the examples here. So this is the altitude versus the averaging kernel. So using this Sentinel-5P Topomi data set, we have validated WAF-Chem like this. So you can see that it is quite reliable. So validation was quite good with very good correlation, as you can see here, nearly 85% correlation for nitrogen dioxide here. So this was one of the current research we did to validate our model. Then there are many other examples, just like the crop burning. So this is the crop database for Nepal, and you can see the open burning of crop residue here with the graph showing mostly the crop burning in the Terai region here. Then its contribution also we looked into using WAF-Chem model like this. And we can see here the blue line in the WAF-Chem, we have taken out the agricultural waste burning, and default is the blue red one. So you can we can see the clear advantage in reducing agricultural waste burning in Nepal. So another example is one of the projects we did, South Asian Nitrogen Hub, where Professor Kulchester was with us. So here also we did study, so it is ongoing, so we have not published yet. So we divided into urban, semi-urban and rural areas. And we looked into PM2.5. So this is the baseline 2015 data set. Then we also are going to find out the attributable proportion for all-cause mortality and so on. So we are doing health risk assessment as well, using the science scenarios, just like how much we can reduce the PM2.5 and its health risk using different reduction scenarios. So I'm not going to the detail of these scenarios, but we can see a clear reduction, just like in this maximum technically feasible reduction. You can see quite significant reduction in the health risk. So to summarize, so air pollution is a critical public health as well as economic challenge, because our economy, just like, for example, the tourism heavily depends on the very clear sky, and one challenge is, of course, the climate and geography in our country plays a big role in this as well. So the country is trying to go for clean energy and electrification of transport. So the government is also going to propose many policies So, of course, to summarize, the local pollution control as well as the transboundary collaboration is also needed in the countries like Nepal. So, thank you for giving me this opportunity. Thank you.
Thank you very much, Kundan. Now we have next talk by Dr. Majar Islam. He is scientist in Soil Science Division of Bangladesh Institute of Nuclear Agriculture. He is very young, talented researcher from Bangladesh, and he will be talking about wetland rice culture, greenhouse gas emission, and its management in Bangladesh. Majar, please.
I am Atharul Islam. I'm a scientist, but now I am a deputy director in BINA administration activities. Now I am working now as additional charge now. So
Very good. Congrats,
today,
actually.
thank you for giving me the floor to present my reviewable presentation. Title is Wetland Rice Culture, Greenhouse Gas Emission and its Management in Bangladesh. So please move this slide. Outline of the presentation, introduction, objective, materials, method, review findings and conclusion. Please, next slide. Introduction and next. The global change, we know what is the global change and global warming, long-term climate change and global change, long-term environmental change and global warming, increased surface earth temperature increase, and it interlinked with climate greenhouse gas emission. And so I please change here this slide present and worldwide greenhouse gas emission prominent by Asia. Here Asia is prominent for greenhouse gas emission. This greenhouse gas emission from agriculture source different region of the world. We know greenhouse gas emission different from different sector. Among them, agriculture is vital sector. Please next. How does agriculture contribute climate change? We know agriculture contribute greenhouse gas emission and which interlinked with climate change. And here, if we consider greenhouse gas emission, then we applied more fertilizer, nitrogen fertilizer, we from cattle house and wetland rice cultivation, and also wetland cultivation act as a carbon store and contribute agriculture 14.5% global greenhouse gas emission from agriculture, and agriculture production instead account for 40% from global food system emission. Please, next slide, please. Here we try to present greenhouse gas emission from agriculture, and from agriculture contribute around methane contribute around 45%, and nitrous oxide 46%, and carbon dioxide 9%. Here there is some cereal crop which contribute vital greenhouse gas emission, rice, wheat, as maize, and figure C shown that rice production how much contribute greenhouse gas emission in Bangladesh. Next slide, please. And rice accounts for 10 to 12% total agriculture greenhouse emission globally. Bangladesh, the 8th largest emitter methane from rice, and rice contribute 23.8% national methane emission. Next slide, please. And here also greenhouse gas emission in Bangladesh percent 40 44.8% from carbon dioxide, 44.1% from methane, and 30.1% from nitrous oxide. From 20 to 29, Bangladesh suffered economic loss of around $3.72 billion for this greenhouse gas emission. Please, next slide. So rice, we know we have limitation, but in Bangladesh, rice is staple food. So we consider how to mitigate this agriculture, and some study already done in Bangladesh, and I present in this review paper what is activity done in Bangladesh. Next, please. So the objectives of my review paper. Next slide. To address the greenhouse gas emission on wetland in rice culture. Next. And to review the mitigate process wetland rice culture in Bangladesh. Next, please. So materials method, we collect, I know what is the, this as a review paper, it is secondary data, and I also, we course instructor and major professor also. Please, next slide. Review of findings. Next slide. So we know the rice cultivation is two types: upland rice cultivation known as Arabic rice, and lowland as irrigated rice or wetland rice. Next slide. So what is the property for wetland rice? We know the in this figure, figure 2, flooding, soil properties, flooding layer and oxalate layer and reduced layer. If you, what is occurred or activities or character after flooded condition for rice cultivation? pH in acidic soil increase pH, and alkaline soil reduce pH. So this is main characteristics of paddy soil or wetland soil. Please, next, please. And we know this slide how the range oxidation reduction potential values in oxidized and submerged soil at which reduction process occurred. Next, please. So greenhouse gas emission, what is process? We know the greenhouse gas emission mainly methane and carbon dioxide in anaerobic conditions. So it is the process. Please, one by one. In anaerobic condition occurred methane and carbon dioxide. How produce methane and carbon dioxide from wetland soil? And we know organic matter process or fermentation process produce hydrogen and carbon dioxide and acetate, and then metagenesis process. That means mitogens and metagenesis and enzyme and produce methane and carbon dioxide. Please, next slide, please. Then methane, and then methane produce methanotrope and methanotropic. This another process. Methane emission occur from by three way. One way from parenchyma cell in plant, and another way evolution from exchange methane from soil to air, and another process. Please, next. Another way, diffusion. We know the diffusion process. Concentration of methane difference, then exchange methane occur. Please, next, please. And how to produce carbon dioxide. Carbon dioxide for interface of anaerobic condition. This process is known as methanotropy, and this occurred by methanotropes bacteria, and this produce carbon dioxide. So it is not related with nitrogen fertilizer, but it depends on organic carbon in aerobic condition. So we blame with on rice cultivation for nitrogen applied from greenhouse gas emission, but not like that. If we keep fallow land, then it will be occurred. So light cultivation is not harmful for us. It act as a source of carbon dioxide or reduce carbon dioxide. Next, please. And how produce methane, nitrous oxide and nitrous oxide. So the anaerobic condition. We know that in flooded soil there are aerobic zone. In aerobic zone, this is occur. This process processes occur. Next, please. Next, it is a lengthy process. So another slide, please. Yes. Yes. Okay. Management practice in greenhouse mitigation in wetland rise. There are several process in walloid practice. Also some research done in Bangladesh. So I have shown in this presentation the fertilizer management. So adjusting rate and time fertilizer application, selection of fertilizer, use of nitrification inhibitor, mycorrhiza, crop test based nitrogen fertilizer option, site specific nitrogen management. Please, next please. And under this management process, what kind of research done in Bangladesh? I have present this table 2. The fertilizer management technique used in Bangladesh to mitigate greenhouse emission from rice field. Here we see if we applied a nitrogen rate less, that mean soil test base, then we reduce nitrous oxide emission and also cumulative methane emission. Next, and also greenhouse gas emission. And the effect of fertilizer seasonal fertilizer emission nitrous oxide in Buro season. Here we use, if we used UDP or INA base, then we see that methane flux reduced by UDP, then other practice. And nitrous oxide also increase in reduce also by UDP. So we consider in this experiment UDP is more effective for reduce methane emission and nitrous oxide emission, and also reduce global warming potential. Next, please. And water management. So there are another process to mitigate greenhouse gas emission, water management. So next, please. Under this process, some research activities done in Bangladesh. So various irrigation management used in Bangladesh to mitigate greenhouse gas emission from rice land, continuous flooding and integrated flooding. So we found that integrated flooding reduced methane emission, and but in this case, nitrous oxide emission increase. So, but if we consider total global warming potential, then we found integrated intermittent irrigation management reduce greenhouse gas emission. Next, please. So some another studies found AWD, that means alternative weeding and drying. Here we found that alternative weeding drying reduce methane emission and nitrous oxide emission as well as global warming potential. Next, please. So tillage practice also reduce greenhouse gas emission. Next, please. So some studies conducted in Bangladesh with these techniques. So table 7, effect of tillage system on cumulative nitrous oxide, methane, and global warming potential. Here we found that strip tillage reduce cumulative methane emission as well as reduce global warming potential. Next, please. So management of soil organic carbon. Next, please. So So soil organic management practices used in Bangladesh to mitigate greenhouse gas emission from rice. And there are several research activities was conducted for this type of research, and here we found urea with voucher and reduce greenhouse gas emission like as methane and nitrous oxide, also global warming potential. But in another, urea and calcium silicate also reduce global warming and greenhouse gas emission. Next, please. Selection cultivar, there are another process to reduce greenhouse gas emission, short durative and high yielding variety. Now I am doing job in Bangladesh in Bangladesh Institute of Nuclear Agriculture. We have many short durative and high yielding variety. With apply this type of variety reduce greenhouse gas emission.
Majar, please complete in 1 minute, please. Huh?
Thank you, sir. Please next slide, please. This is a whole process at a glance for mitigating greenhouse gas emission. Next, please. So, conclusion. Finally, we conclude that wetland ecosystem contribute most to worldwide rice cultivation, flooding, altered chemistry of wetland rice, affecting physical, chemical, and biological properties. Lowland rice paddy mainly contribute to methane emission and also release nitrous oxide and carbon dioxide due to microbial activities. But modification to traditional management strategies process a huge potential to overcome greenhouse gas emission in wetland rice culture among different approaches: fertilizer management, irrigation management, tillage management, management of soil, organic carbon, selective, suitable cultivar, mitigate greenhouse gas one. Therefore, knowing the mitigation of greenhouse gas emission from wetland rice feel important to develop strategies to reduce greenhouse emission from rice cultivated soil. Next. So thanks to all for fashion sharing.
Thank you, Dr. Majorul Islam. I have.
Please for me, I have limitation of time due to I have administrative activities. So
just I have one question.
okay, sir.
Please, how you correlate your work with air pollution?
Yes, sir. We know that air polluted occur different sector related for air pollution like a transportation, industry, buildings and power station, agriculture and waste management. So agriculture contribute greenhouse gas emission which interlinked with air pollution.
Okay, we can discuss and you try to correlate more on air pollution. Your work, you are in hurry to go. Thank you very much for speaking at this forum. Thank you, Major.
Thank you, sir. Can I leave this
yeah,
session?
you may leave now. Thank you.
Thank you, sir. Thank you, sir.
Now we have next speaker, Dr. Yu Chen Wang Mia. She will be speaking on Taiwan MPL network long-term observations and their applications in the aerosol and binary layer studies. Mia is a postdoctoral fellow at the Atmosphere Science Center and NCU, Taiwan. She's contributing to that network what Professor Carlo is having. Mia, now floor is yours. You have 20 minutes.
Good afternoon, dear audience. I'm from India and Taiwan and other country, and I'm Yuchen Mia Wang from National Central University. And today I will present the Taiwan MPL network long-term observation and their applications in aerosol and boundary layer studies. And this talk focuses on how long-term MPL observation in Taiwan are used to investigate the air quality and the air pollution from vertical measurements. And I will also introduce the global and Taiwan MPONet in its collaboration, capability, and application in detecting the aerosol events. Okay. The first, Taiwan is influenced by both local air pollution and pollutants transported from the outside the island, including Asian dust, biomass burning, and haze from East and Southeast Asia. And these pollutants can reach Taiwan under different weather patterns and often appear as layered structure in the atmosphere. And as shown in this figure, in the bottom figure, surface air quality is affected not only by emission sources, but also by atmospheric dispersion conditions. The near surface winds control horizontal ventilation, while the vertical structure of the lower atmosphere determines vertical mixing. And when vertical ventilation is weak, pollutants accumulate near surface and resulting in poor air quality. And in here, and in Taiwan, the ground-based air quality monitoring network provides an important information on surface air quality and regional pollution patterns. However, they cannot show how pollutants are distributed with height in the atmosphere. And in the central and the southern Taiwan, PM 2.5 and PM 10 pollution occur frequently. Besides the local emission source, weak dispersion and stable boundary layer condition often limit the vertical mixing and causing the pollutants to accumulate near the surface. And to better understand this process, vertical aspirations are needed. So the optical remote sensing allows the long-term continuous monitoring of aerosol with height and provides useful insights into the the time, and the change of the air pollution. And this figure showed different observation platform used to study air quality and atmospheric structures, like satellites, radio sounds, and the UAV system. UAV systems provide useful information. And by combining this platform with the ground-based aerosol LiDAR and the sound photometers, we can build a dimensional observation in Taiwan across the height, space, and the time. And this approach allows the continuous monitoring of vertical aerosol distribution and boundary layer processes, which is important for understanding air pollution and its transportation and transition. And so for the aerosol LiDAR, the micropulse LiDAR, also called the MPL, is a ground-based active remote sensing system that uses elastic backscattering. And the optical design of the MPL is shown in the right panel. The optical design here. And its use of 532 nanometers micropulse laser operating at 2500 Hz allows continuous and vertical observation of the aerosol. And the MPL provides aerosol profiles with high time and height resolution, with a vertical resolution of 75 meters and a temporal resolution of the 1 minute. And it uses low power and is eye-safe, so making it suitable for long-term and unintended operation. And the main data products include the NRB and the depolarization ratio. The normalized relative backscattering shows the relative amount and the aerosol vertical distribution. And the depot ratio shows the information on the particle shape and can help identify the difference of aerosol type. And in the MPL network, the NASA micropulse LiDAR network is designed to observe aerosol and cloud for climate change and air quality studies. And one of its main mission is to provide ground-based observation that supports NASA satellite missions through the validation and comparison. And MPLNet data are also used to develop aerosol forecasting model and automatic classification algorithm for aerosol clouds and precipitation. And these long-term standardized observations are essential for both satellite and model application. And in Taiwan, The NPL network currently includes 4 fixed stations. And to strengthen the partnership between Taiwan and US, NASA NPLnet has designated the APNCU as the Asian reference site in the 2020, and recognizing the role in providing high quality and reliable LiDAR observations. And so in our regular on-site maintenance and the component replacements allow the rapid recovery of the continuous observations. And hardware calibration using optical bench systems correct the instrumental errors, and while vertical profiles correction with a wide field receiver improve data quality near the surface. And in addition, the data profiles are intercompared at the reference sites to ensure instrument performance can consistency across station within the network. So in our station, we can this is our standard instrument, and we can put another instrument to do the parallel comparison. So one of the important application of NPL is to retrieve the PBL height, the boundary layer height. Okay, the PBL height is estimated from the aerosol vertical profiles observed by NPL. Because aerosol concentrations often change sharply at the top of boundary layer, the LiDAR provides an effective way to identify this transition. In this study, several retrieval methods are applied, including the gradient method, for example, like here, and the depolarization ratio threshold method in this panel, and hybrid image processing techniques. And combining this method allows for more robust PBL height estimation under different atmospheric conditions. And in my own research, I further use this observation from all the NPL sites in Taiwan to examine the seasonal characteristics of the PBL heights across the different geographic environments. And this work will be published as a journal paper soon. And here, this figure show an example of vertical misting observed by NPL under the return flow of a high pressure system. And during this period, the weak dispersion and the lengthy breeze effect lead to pollutant accumulation over the western Taiwan. As marked by A, daytime heating increased the PBL height to above 1 kilometer, enhancing the vertical mixing and slightly reducing the surface PM2.5 concentration. And at nighttime, the PBL height decreased, while a residual layer aerosol remains around 1.5 kilometers. On the following day, the part of this residual layer mixed downward into the growing boundary layer, increasing the near surface pollutant levels and the PM2.5 concentrations. In this case, clearly demonstrate how boundary layer development and the vertical mixing control the near surface pollutant accumulation. And under these similar synaptic conditions, even stronger accumulation can occur. In this case, a decrease in the potential. Here is a UAV observation. The potential temperature is the solid line, and the color shape is the PM2.5. So in here, a decrease in the potential temperature with the height indicates a stable atmosphere. So near surface, the temperature inversion typically form at night and in early morning, strongly limiting the vertical mixing. And during the night and the early morning, for example, like here, the PBL height was only about 300 to 400 meters. So strong temperature inversion combined with the weak wind decreased the vertical dispersion and leading to the severe pollution near the surface. And the PBL height and the pollution layer observed by NPL is shaded is RNRB, and the line is the PM2.5 from the UAV observation. They agree with each other. And the PBO signal clearly showed the boundary layer development under these stable conditions. And another case is here show two examples of the long-range transport events affecting Taiwan. The first case, the pollutants were transported to Taiwan by easterly winds at around 3 kilometers. So at the Mountain Luling, the Luling atmospheric background station, you can see the increased concentration of PM, the carbon monoxide, and the methane was observed in this case. And LiDAR depot ratio here, from the northern to southern Taiwan, LiDAR depot ratio profile showed a higher value between 2 to 6 kilometers, together with a clear downward transport signal, indicating the influence of the long-range transported aerosol in the upper level. But in the second case, the high depot ratio below 3 kilometers suggested non-spherical particles. A strong northeast surface wind transported the dust from the outside Taiwan and into Taiwan. And this was further confirmed by the simulated increase at the ground-based dust monitoring station. Even the dust station, you see the same patterns. Okay, so identify these events as a long-range dust transport in a lower level. So here's another case for the fire events. So not only from the long-range transport or local emission, also this kind of local fire events, we can detect that. So on the March 14, the 22nd, a fire broke out from a factory about 5 kilometers south of NCU station at 7:30 a.m. And the 6 more rapidly rose, and the all-sky camera image show you can see the smoke appear here. And around 8 a.m., the LiDAR show high depot ratio appear here, and also the PN10 increase at the same time. So, and from the AOD from the sound parameter and the AE from the sound parameter, we can see the AOD increase and the AE slightly decrease. Okay, so it's suggesting enhance the aerosol loading and the aerosol the particle size is increasing. Okay, and after 10 a.m., the pollutant dispersion reduced near surface PM, but the PM remains at a low at night, but the smell of the smoke continue under the weak winds. So to conclude, this figure summarizes the key contribution and the application of the Taiwan micropulse LiDAR network. And the long-term LiDAR observation provides a detailed vertical information on the aerosol and clouds. And these continuous measurements can strengthen the ground-based three-dimensional remote sensing and support the air satellite data validation. And second, the network includes 4 permanent stations that enable long-term continuous monitoring. Regular hardware maintenance and the data intercomparison ensure the quality and high quality updation and making the network a reliable reference in Asia. And third, the LiDAR data are widely used to estimate the boundary layer height structure and track the aerosol transport from local and long-range sources, and detect the episodic events like fire events or volcanic eruptions. And then finally, combining the ground-based LiDAR with the satellite observation and the model simulation improves air pollution monitoring and forecasting, and support the advance in cloud classification and precipitation detection. So the overall, the long-term PBL observation are a powerful tool for studying aerosol boundary layer interaction and support air quality and climate research in Taiwan and Southeast Asia. Okay, that's all. Thank you.
Thank you very much, Mia, for timely completion. If anybody having some query, please write in chat. Now, our next speaker is Dr. Arjit Malik. he will be talking about metal organic framework functionalized products for pollutant removal. Dr. Arjit Malik, he is
Yes.
my colleague at SCS JNU. He is very young and dynamic, working on carbon capture, so he can help in air pollution control technologies. Arjit, please.
Good afternoon, everyone. Myself, Dr. Arijit Malik, so Assistant Professor, School of Environmental Science. So thank you for giving me the opportunity to present my work in this fantastic platform. So today's topic is metal organic frameworks, functionalized product for pollutant removal. So at first, I want to show the data of WHO, which represents that more than 7 million deaths per year is happening due to the air pollution and related diseases. And most vulnerable situation, we can see the Southeast Asia, where the more people can be affected due to the air pollution. So in this scenario, we can think about some solution. So there will be two solutions. Number one solution, we need to reduce the air pollution by human activities. And one more solution is that we need to find out some way to purify this air. So if you see in our market, we can see different types of air filter or air purifiers are present. And if you see here, in the air purifier, it is a very simple system and it has some filters. And the number one is the pre-filter, where you can see it's generally filter out the primary particles, bigger particles like hair or feather. And the second filter is the main filter, which is made of nanofibers, and they can actually separate the smaller particle like particulate matters, like around 3 micron size particles. And the number 3 filter is the activated carbon filter. Activated carbon filter are mainly for the removal of poisonous gases like nitrogen oxide, sulfur oxide, and volatile organic carbons. So, but the problem is that putting too many filters really create obstruction for airflow. Also, the activated carbon are not the proper candidate to absorb the VOCs and the poisonous gases. So in this context, the metal, there are different porous materials are present, like porous carbon, zeolites, porous polymers, and also metal organic frameworks. And metal organic frameworks are one of the most promising candidate in that case, because it has crystallinity and high porosity. And the pores, you can functionalize the pores based on your needs. Like we want to capture one of the VOCs or any type of poisonous gases, especially the sulfur dioxide. Sulfur dioxide is one of the harmful gases that we need to purify. So if you see what is metal organic frameworks, in physically they are powder like chalk dust type of you see. But if you see in microscope, they are very nice crystalline shape. And if you see the single crystal image, then you can see it's a network like a structure, and it has some porosity. And this network made of the organic linkers and metal ions. Okay, and these material are one of the best candidate for absorbent material. So it can either store the poisonous molecules, or it can also separate. Okay, but the another part is the nanofibers. Okay, and these nanofibers are made of polymer nanofibers, which generally pass through from a needle and then electrospinning on top of a surface. So these nanofibers are cross-linked and forms this filter. But now, if we want to reduce number of filters, so here our concept is to combine the nanofibers and metal organic framework together. So if you see, the polymers are pan polyacrylonitrile and polystyrenes. This type of polymers nanofiber generally used in the filter. Now, if we mix the metal organic framework and the polymer, and then we make a nanofiber, so in that case, you no need to use the double filter of nanofiber and activated carbon. So these nanofibers will work for both the cases. So it will be nanofiber as well as there are absorbent molecules present into this fiber. And one more interesting thing is that if you see the surface of the nanofiber is too smooth, so when the particulate matters interact with this fiber, they sometimes get reflected. But when the MOF and these polymers make nanofiber, you can see the surface of the nanofiber is very rough, and they have now the anchoring site to the particulate matters. Now, how to make the setup? So the experimental setup will be a box which will have a fan, and the polluted air can go from this side, and here will be the MOF nanofiber filter. And when the purified air can we can get this side. And this is one of the fantastic work by Bo-Wang groups, and they have shown this nice setup where we can actually burn a cigarette in one side, and you can get the purified air in the other side. Okay, and where the MOF particles are embedded in the nanofiber. So, and you can see after the filtration of the particulate matters, how these particulate matters are attached to the nanofibers. And if you see the real data, you can see these MOF fibers are really performing better than the normal the polymer fibers. So that's why since the network is full of roughness on the surface, it can actually attach the particulate matters with the fiber. In our lab, we have also made an important MOF which have amino functionality, NH2. So, and that's why it is so important that it can selectively catch the sulfur dioxide. Okay, and also it has very good interactions with the VOCs. And it has very nice porosity. This pink ball and yellow balls represents the void inside the metal organic frameworks. So it had a tetrahedral and octahedral void. So these MOFs are very porous. So how we see that it is porous, and also they are very thermally stable. You can see the TGA analysis of this material, and around 250 degrees Celsius, this material is very stable. And the PXRD shows it is highly crystalline. So highly crystalline and very much thermally stable. So these materials are made for very good adsorbent. Now we'll see, is it porous or not? So if you see the single crystal structure, and then you can see there is some porosity. But when we did the gas adsorption studies, like nitrogen adsorption studies, and we can see this material can have surface area around 680 meters per gram. So you can think about how porous it is. So one more model experiment we did, we take this material and put it into a dye. And when the dye, within few minutes, the dye molecule absorb into this MOF material, and you can see the distinct color change. Okay, so from white it become, after absorbing the dye, it become yellowish or reddish. Okay, so based on the different dyes. So these molecules are the very good adsorbent. Now our new idea is to, instead of making a composite, we will grow the MOF particle on top of the nanofiber. So in that case, you will see the MOF, the fiber roughness will be very good. So it can have better performance compared to the normal nanofiber. And also this type of fiber can not only use for the air purification, you can use for making mask, the N95 type of mask, Okay, and even the AC filter, we can put this type of filter to the indoor, if any there is particulate matters or VOC. So both of the things, it will work, the one fiber will work for the both the things. Okay, so in conclusion, we made a MOF which can functionalized, and then it have very good crystallinity and porosity, and this can absorb model pollutants like dye. And if we can make, now we are trying to make fibers which will be very good for this type of air purification setup. So at the end, I want to acknowledge the JNU for giving me the facilities, and AOGS and TSU give me the opportunity to showcase my work. And I will conclude with a comment by Ban Ki-moon. So he said, the climate change is the defining issue of our time, and we are at the defining moment. So thank you for listening my talk.
Thank you very much, Arjit. Wonderful, a new dimension of this forum. We can help in controlling pollution. Now we have next talk by Dr. Manish Naja. Manish, are you there? No?
Yes. I'm trying to share this slide.
Thank you very much. And Dr. Manish will be speaking on long-term changes in trace gases and aerosols over the Himalayas in situ and remote sensing observations. For a brief introduction, Dr. Manish Naja is the director of Aryabhat Research Institute of Observational Sciences, ARIES, in Nainital, India. And also he is a member of different advisory groups and co-chair of IGAC Mongo, Monsoon Asia and Oceania Network Group. Manish, please go ahead. Thank you very much.
Thank you very much. And I thanks organizers from both the sides, from India and Taiwan, for giving me this opportunity to talk to about this activity, particularly observational activity which we are carrying out in the Himalayan region. And I will be presenting on the study on the trace gases and aerosol, and using both in situ and the remote sensing instruments. And here I'm trying to show the observation side. On the figure on the left hand side, so is showing our institute in Nainital, which is located in the Himalayan region at the altitude of around 2000 meters. And we have another campus which is on the right hand side at the altitude of around 2400. So we are basically located in the Himalayan region, and we have the two research divisions in atmospheric science. So I'm focusing on the atmospheric science activity here, and observations of trace gases, aerosol, meteorology, and dynamics. And here in this slide, I'm the why the importance of this location. And if you see on the light on the left hand side, this is the basically we are located in the Himalayan region. So the whatever the pollutants from the Gangtok plain or the pollutant in the IGP, they are reaching to Himalayan region. And if you see in the back the analysis, and that shows for our location how the air mass from different region reaching to this location and during different time. Like if we start with the winter time in the January, like air mass even coming from the Africa and Europe, they are reaching to our location, and we have seen with the observation and evidence that the some fine mode of particles are aerosols, and some of the gaseous component which is in the high longer length residence time, they are from the northern part of Africa and southern Europe, they are reaching to the Himalayan region. And if you come on the May, which is basically representing the springtime, the air mass is circulating over the region. So this is the basically period when you have the stronger influence from the local pollution from the IGP. IGP basically we call the Indo-Gangetic Plain, which is the highly polluted region in northern part of India. In September, again it is basically the monsoon. In monsoon time, very clean air or the air coming from the sea and display. This is the mode of transport from Bengal. Another thing in this part of northern India, we have or the forest, which peaks in the one bottom figure on the left hand side, which peaks in March and May. So you have of the trace period. So basically, in this part of India, in the northern part of Himalayan region, you have the combination of the regional pollution emission, you have the biomass burning, you have the long range transport, and this is also the region of the convective activity. So you have the convective uplifting from the surface level, the pollutants they go up. And of course, we are in the Himalayan region, so the background level is also there. And this region, our location, is also the region the ITCG reaches this side. So the dynamics is also playing very role. And AC summer monsoon anticyclone is also very much active in this part. And here I'm trying to show the observational facility at our region Nainital. We have the surface-based observation, we have the balloon-borne observation, we have the LiDAR, and we have radar. And here on the top right-hand side, we are showing one of the unique facility in this location. We have the radar, and which is capable of measuring the range from surface to almost 20 kilometers. And this is we can have the continuous observation. We have the several trace gases like ozone related precursor gases, and we have the greenhouse gases. We have the aerosol observation, and recently we have also started observation using the spectroscopic observations using the MaxDOS and the Pandora. Now, considering the importance of in the north part of India, the lot of international field campaign are also conducted. And a few years back, we had the one campaign that is the part of the Stratoclim project when we have a lot of surface and the balloon one observation are carried out in collaboration with the ITM Pune group and the Zurich Institute. And a lot of balloon flights were conducted using the water vapor, ozone, and the aerosol for the cobalt, and the water vapor CFS based sensor is also used. And this campaign was conducted again in collaboration with the or simultaneous observation conducted over the Garanki region and the Lhasa. So we have the coordinated experiment in this location. Another campaign, we participated in the SysCat campaign. Basically, the main idea was to see how the pollutants is outflow from the northern part of India and reach it to the South Asian extended region. Particularly, our focus was on the Kathmandu Valley. So, a lot of institute from the different country participated in this campaign, like from Nepal, Germany, Korea, and China, and of course India. So we have a lot of experiment, but we focus on the aerosol and trace gases, and with this experiment, the LiDAR and some of the stations we also. This is another campaign which conducted in our location. The photograph from the campaign is conducted is Nainital. Collaboration with the Department of US AR facility. So they brought a lot of content at this location, and the collaboration in the organization and IS. This was conducted and the understand how the pollution from the region is up, but redistributed at the higher height. And we have got a lot of information on the influence, how the region influence over the region, and some of the detailed information on the aerosol composition and the CCN formation also seen. So this was this campaign. Now here I'm coming to the our study which we conducted, and this is the one snapshot I'm trying to show for the aerosol study. We have the aerosol observation since 2002, and basically with black carbon and the aerosol optical depth observation started, and then later on we have added other aerosol component observation, elemental carbon, organic carbon, and now have started the APS also, and the nephelometer. We have a lot of instrument observation. Now here I'm trying to one the trend which is the longest the observation of black carbon over the mountain in the South Asia. And on what you see in this north part of India, condition, the black carbon is showing the somewhat the decreasing trend. And this is one interesting I'd like to cover, like the reanalysis data, they are not in agreement. So one to see how this observation is basically put in the proper reference. So they again, like if you see, this is again representing from the Himalayan region. Now, what is the situation that one has to find out? And we have also see here on the how this observation of black carbon is going to influence the radiative forcing. This is radiative forcing, and you can see very clearly, like the we have the observation of elemental carbon, orange carbon, and those data were used for correction of the of the black carbon observation, and you can see the difference in the radiative forcing, the corrected one, and because of that correction, you have the slightly more the higher value of the radiative forcing. Similarly, we also have the surface ozone observations from 2006. On the panel on the right hand side, to show this the trend in the surface ozone. And if you see the continuous data, it looks like the trend is not very clear, but very clearly seen the surface ozone is so very slight decrease or no trend up to 2016. But after the very clear increase in the surface ozone. This is the again in implement the changeover of the pollution or the fuel which is used in the different transport. So like changeover the implementation of CNG and other species, and that is basically we can see here. And what is our assumption in case of surface ozone? It is very much important whether we are in coming which regime, whether it is NOC limited regime or BOC limited regime, and very clearly seen like after 2016-17 that the chemistry portion is changed, and you can see some buildup in the surface ozone in this part, and this is very much significant. You can see in the mean value of the increase in ozone is around 1.27 ppb per year, and again this increase is much higher at the higher level of the 95 percentile. Now, we also have the lot of experiment, the observation from the ISRO network around the 20 sites in India, and this surface ozone data is used to make assessment how the high level of ozone is influencing or the on the reducing the the growth of the wheat and rice. Now it is well established or well known feature like high level of ozone can reduce the growth of the vegetation. And here this is an observation based the outcome, and you can see if you divide in the India in different parts, and you can see the northern part of India using the EOT40 method. Of course, there are two methods, EOT40 and M70 method. And using the EOT40 method, you can see over Indian region almost 8 to 9 million ton of the crop loss of wheat is can be seen with the high level of ozone. If you see in the rice, this loss is around 2 to 2.5 million ton of the loss in the case of the rice. So there is direct evidence that observational evidence that the high level of ozone can lead to such of reduction in the crop growth. Now, we are also having the greenhouse gases observation, and here I'm trying to show the snapshot of the some of the greenhouse gases like CO2, SF6, or the methane and N2O. And as you can see in the this Himalayan region, very clearly the CO2 levels are increased. Of course, this is a global phenomena, but again, I would like to draw your attention here in SF6. SF6, which is in the PPT range, so I'm sorry, this is written wrongly, PPP, it is PPT. And when we started this observation SF6, the SF6 level was in 2006 was around 6 ppt. Now in the present time, this level is touching to almost 12 to 13 ppt. And so this is very much alarming because if you see the global warming potential of SF6 is very much high, but only because this mixing ratio of concentration is very low, it is people are not much worried. But one has to see in the long run how it is going to influence. And methane, which is again showing the large increase now in this Himalayan region, methane level is almost touching to the, I mean, in the background condition average level is touching to almost 2 to 2.1 ppm. And N2O is also very showing very much significant increase. Apart from that, if you see in the middle portion, the seasonal cycle, the amplitude of the CO2 in this part of in the India in the Himalayan region is very large, even if you compare with the Mauna Loa. The black color is with Mauna Loa, where the peak to peak amplitude is only 10 ppm. But in this Nainital in the Himalayan region, this peak to peak amplitude goes almost the 30 or even in the 35 ppm. And that is because of the very large vegetation in this part of India. We also initiated the observations of the spectrometer-based observation of some of the trace gases, aerosol, because some of the gases or the glyoxal, they are very difficult to the traditional method. So we have two instruments, the Pandora spectrometer and the other is the Mac. They are located at the two sides, one is the mountain side, another is the plain IGP region. The another important aspect of this observation is also the validation of these satellites data. There are many satellites are doing this observation of NO2 or the formaldehyde or dioxide. And now what I'm trying to say, the importance of this location in the Himalayan region. So because of the complex topography, the satellite observations are having a lot of uncertainty in the lowermost layer of the atmosphere or in the boundary. And here I like to show this very well how the importance of the ground observation. Here is the company max dose observation, which is the site in the plain region and the Himalayan area, which is around 400 meters. And this is a comparison using the and the GO, NO2 and the SO2 and formaldehyde. If you see the most of this is like SO2 or formaldehyde, the satellite observations the negative bias. The variation is somewhat negative, but the GO data they are much lower than the max dose. So looks like the satellite data at IGP region is showing the negative bias. But now the interesting point, if suppose we do the same comparison of validation at the mountainside in the Himalayan region in Nainital, just one or two more slides. So very quickly, we also conducted one in the high mountain region, and what is the main important point I will to show? Like even the Himalayan region, when we went from the Nainital to Munsiari, which is altitude around 3,500, the level of the VOC, they are higher than the Nainital. So I'm trying to show the influence of the transport from the different region is very significant over this region. And here I will just skip this slide and I directly come to this one of the important slide. Like we conducted this, I said we have the BOC observation, and we are trying to show how this BOC is having the impact on the human health risk and even crop loss. This is the one slide on the ozone observations. We have a lot of observation, and I'm trying to show the high vertical distribution showing the impact of the biomass burning even at the altitude of around the 6 to 10 kilometer height. Yeah, so this is the second last slide. We are also planning one campaign and different observation of aerosol even in the deeper Himalayan region with a lot of new instruments. And with this, I would like to thanks and just with the trying to show this is our institute at the mountain region, and you can see a lot of cloud in between. And so this is the basically natural laboratory in Himalayan region, and that's all from my side.
Thank you very much, Dr. Manish, for your valuable contribution. And sorry for interruption, something happened online. But definitely your input is going to help AOGS, RAC, Air Pollution Working Group of this. And overall, because you are very old, means colleague of mine since Indo-X, and so lot of work having lot of importance. We will be in touch. And now next speaker of this session is the last speaker, Dr. Prasenjit Acharya. He will be talking on response of agriculture yield to the variation of meteorology and air pollution in the Indo-Gangetic Plains, implications of future climate change.
Is it fine? Okay, fine. Thank you, Professor Kulshrestha and the Professor Wang for giving the opportunity to talk in this second BIT forum. And I'm also thankful to Professor Naja for making a wonderful background to present my work. What I'm going to talk about this afternoon is that what is the probable implications of the meteorological variability, including the air pollutions, to the rice yield variations across the Indo-Gangetic plains. Okay, so we have globally it was observed that the combined effect of air pollutions and the climate change has a severe threat. So the estimations which was reported earlier that suggest that it was about 37% reductions in some of the cereals, major cereal grains, or per degree increase of the temperature. And the combined effect of the temperature and precipitation was also reported that it reduced the yield for the maize and wheat up to 45%. Turning the lens to the air pollutions, it was estimated that about 0.21 to 0.1 to 0.22% in reductions has happened per 1% increase in the particulate matter. Now, these are the parts and parcels of the findings that was reported in the earlier studies. So we choose that region as it is one of the principal rice growing region of the world, which holds nearly 27% share of the cultivable area in India and about 52% of Indian cereal productions. And if we look into the global context, this region is about sharing 14% of the rice and about 7% of the wheat to the global food. And if you look into the South Asian context, it's home to about 57% of the rice wheat system, which turns this region extremely important for the regional level food security. So on the left side, we have did the analysis back in 2020. It's just the air pollution level from Morris and MISI, which suggests that yes, the entire Indo-Gangetic plain is having very high degree of aerosol optical depth, suggesting we have a high pollution load in the Indo-Gangetic plain. It's and it is configured by the topography of these region. So objectives of this work is to map the effect size of the meteorology and the pollution parameters, testing the regional scale response of the agricultural yield, focusing on the monsoon rise, and to estimate the sensitivity of the agricultural yield to the potential pathways of climate change. We're gonna we have applied the received the SSP2 and SSP5 pathways, potential pathways of future climate change. So we skip that. So the roots of the study actually dates and roots of the study actually ingrained in these yield pattern, and these yield pattern is actually from all major districts in the Indo-Gangetic plains in India. And we can see that starting from 2004 to 2019, it is continuously increasing. And when we look at that, whether we have any breakpoints in this increasing tendency, the breakpoint suggests that we have a change point at around 2010. And when you break these entire series into two groups, prior to 2010, after 2010, we have seen that yes, if we break it, let me just show you that if we break that, we did not get any significance results, as well as also not significance results after breaking. This is before breaking, and this is after breaking. But if we do analyze the entire series, it is appearing. It shows that it is statistically significant. I mean, in terms of the increasing trend. So we observe that pattern and look for the reasons why it is so fluctuating in this window, and that's where we confine our analysis. So it all started with defining the rice field. So it includes the both irrigated and rain-fed agricultural system. We use sort of spectral thresholding methods to map the rice field using the sort of matrix called normalized difference water index, assuming the fact that the rice field requires the flooding conditions there for all rice fields where the NDWI value, normalized difference water index value, is greater than 0. We detect them as a rice field, and then we extract the statistics from there and compare it with the statistics from the government agency and try to find out that what the level of association between them. So once we satisfied with that, when we then deploy some of the covariates, environmental variables, that is gross primary production, interactions of soil moisture and fertilizer, one spectral index of EVI, then evapotranspirations, and the mean temperature, because they are the vital for the growth of the rice. And against we have our the dependent variable, which is the yield statistics at the district level. So we run a random forest regression functions, and then we map it at the cellular level, the grid bus level. So this pixel size would be around 500 meter, and this is how it looks like. So once we map this agricultural yield starting from 2004 to 2009, that gives us a baseline to apply the models for understanding or decoupling the air pollution and the meteorology and air pollution effect. So we then use this to decouple the effect of meteorological variability and air pollution. We follow the simple linear integration models. The first one is our baseline model, which only we only take the time as a functions, okay, and then we use the sort of meteorological variables at the maximum temperature, precipitation, and surface solar radiations as a second model, standing for the meteorological model, and then the third model, which stands for the air pollution model, where the aerosol optical index in ozone, surface ozone at 975 hectopascals, close to the surface, not exactly, was used to model the agricultural yield. Okay. So and the reason why we choose the linear model, yes, there are complexities in the distributions, but we followed these histograms and observed that perhaps the linear function will give me the more interpretable results, right? And this is on the right side, what you are actually seeing the temporal patterns of all the explanatory variables that we have used in this in decoupling the effect, where this is a region ID, where the TGP stands for the western part, that's a trans-Gangetic plain, UGP stands for the upper Gangetic plain, this MGP middle Gangetic plain, and LGP is your lower Gangetic plain, which I have in fact given you the indications right here. Right? So this is a TGP, UGP, MGP, and this is a LGP. So once we analyze that, once we model that rise at the grid level, we then go for finding anomalies, and we observe that anomalies of the rice yield, and we observe that as we move from 2004 to after 2010, there are negative anomalies before 2010, and there are certainly the positive anomalies in after 2010, and we see that in 2018, 2019, there are occurrences in the negative anomaly yield. Okay, so we try to understand that what happens to, after 2010, why such fluctuations are there, and we run we use the air pollution model and the meteorological model together, and pixel level regressions, and that suggests that this is the effect size, that is the beta coefficient, the slope coefficient for the entire IGP, and this is just a zonal statistics that we have built from this modeling. Okay, so out of the all both meteorology and air pollution effect, we observed that the temperature and AOD has a very decisive role in altering the agricultural yield, where except the LGP, for all other agroclimatic region, we have seen the negative effect of air pollution effect, and we also observed the notable negative effect of the surface solar radiation, as the intense solar radiation is responsible for the alteration in the biological cellular. I guess so. It causes the cellular damage as well as the early grain filling, and it also increases the evapotranspiration rate, therefore causing the photosynthesis process, affecting the photosynthesis process. At the same time, we also see that despite having despite having the reported damaging effect of O3, surface O3, except the LGP, all of the other regions have a positive association with increasing O3. And that just poses the question why such things are happening. And turns out it turns out to be that it could be the CO2 fertilization effect that might reduce the potential damaging effect of O3. So once we estimate that effect, and then we model the first component of yield, and then use the equation 4, which I have shown you earlier, to model the estimated relative yield change. So that's the pattern of relative yield change. The left side suggests you the meteorological effect, the right side shows you the air pollution effect, and that's the estimated effect of the reduction of the relative yield due to the meteorology and the air pollution, which is about 10% reductions has been registered for all, except for the LGP. For all other regions, we have registered a significant reductions in the yield. Now, when we when you roll these model with the SSP scenarios, this is what we have obtained, and that suggests that the both transgangetic plain, upper gangetic plain, and the middle gangetic plain do register a significant reduction, which amounting to 25% to 50% reductions in the yield. However, the lower gangetic plain doesn't show that. Instead, for both air pollutions and meteorological, the lower gangetic plains suggests that it withstands both the variability, and that's suggesting that LGP could potentially show the resilience in terms of rice yield in facing the potential future climate change pathways. So I'm going to end up with these things that that if that is our estimations, so it has a serious implications on the South Asian supply chain of rice, because that's if all other, as I mentioned earlier, that it's about globally the 40% rice has been supplied from this region, and it homes about 57% of the rice wheat system. So if the other regions except LGP suffers badly from the potential climate change effect, then it's definitely going to affect the sending the rippling effect to the supply chain of rice. But that's it from my side. Thank you so much.
Thank you very much, Dr. Prasanjit, for your valuable input. Now we are summarizing technical session 1. We had wonderful talks and new insights about air pollution in the Indo-Pacific region, starting from overview of this region, overview on air pollution in this region, to having expertise on long-range transport and calculation on population-weighted PM 2.5 exposure, then risk assessment, and also the chemical speciation and aerosol profiling on about dust BC sulfate, that expertise we have. And then there are expertise, people talked about that, about LIDAR measurements and metal organic framework to remove pollutants from air, then monitoring and measurement new insights about transport of air pollution from Middle East to Himalayas and air pollution effect on agriculture crop yield. And there were some discussions about some bottlenecks, for example, data sharing problem in Pakistan, then transboundary pollution issue in Pakistan, and also a common need right here out of this is the need of hybrid monitoring station, coupling with the ground-based measurements and remote sensing measurements. So with this, I thank all the speakers, attendees, and also our chairman, Professor Ip and Professor Sattu. Thank you very much. And we will have break of 20 minutes. And again, we will assemble at 1:05 Indian time, and Taiwan time is 15:35. Next session will be chaired by Professor Carlo. So thank you all. We will meet at 1:05. Professor, if you want to say something.
Oh, just say want to take a break,
20 minutes.
Yeah, and come back and have coffee. Yeah.
See you.
Good afternoon, everyone. I think the time's up for our today's second session. So I'm going to chair this session. We have 8 speakers, and I just want to remind you every speaker have 15 minutes. So I will give you some sign. 30 minutes, so you have 2 minutes to wrap up your presentation. So I hope I can handle everybody's presentation on time. Okay. So our first speaker is from China Medical University, Professor Bin Feng Huang. So he's going to give us a presentation titled Satellite driven the particle matter exposure in pregnancy and infancy and the risk of allergic diseases in Taiwan. So let's welcome. Thank you. Time's yours.
Thank you very much. It's my pleasure to share our study, PM 2.5 during pregnancy and infancy, on the risk of the allergic disease in Taiwan, and how to make the next. So I mainly will focus on 3 allergic disease. One would be the asthma, then the other is allergic rhinitis and atopic dermatitis. Then, in Taiwan, there are only 77 air monitor stations in Taiwan in 2004, but the spread is a little bit narrow. Somewhere more, but the other side, particularly for east side, is very limited. So our approach is using satellite base with so-called AOD from NASA. Then it's the 1 by 1 kilometer resolution, and they will give us around 36,000 pixels. And when the satellite passes the Taiwan, then we can have the AOD's measurement. Then we try to incorporate the land use as well as the weather forecast parameter. Then integrate our ground level PM 2.5, then using the AI approach to predict the PM 2.5 for each 1 by 1 kilometers resolutions. So we also have a tenfold validation, then try to do the exposure assessment surrounding in Taiwan. How about next, please? Next, please. So there are some meteorological variables, including total precipitation, temperature, dew point, and so forth, and also then used for commercial, temple, industry, and so forth. Next, please. So we try to integrate AOD, meteorological, land use, and also we need to consider the cloud fraction because the satellite image were influenced by cloud fractions. So after that, we try to build up the exposure pollutant bank from 2004 through now. So that's our main idea. The next one, I will show you. Next, please. Next one. That's our XGBoost prediction models. Y is the PM2.5. The X is the explanatory variable, including AOD, boundary layer, and so forth. So that's our final prediction models. Then how about the result? Next. We get start from 10 kilometers, I think 10 years ago, then 3 kilometers, then now is 1 kilometer. So when you check the CVR square, the increase substantially, it up to the 0.9, and the CVRMSE is only 0.52. So this model shows us surrounding Taiwan, we using this approach daily base, and 1 by 1 kilometer can produce very good performance, particularly in the PM2.5. So that's our exposure assessment bank. Then how about the health outcomes? Next one, please. We try to get the data from our health insurance, the so-called birth registration. So we can build up a birth cohort from 2004 to 2015, and each child we can follow up until 5 years old, and check up asthma, allergic rhinitis, and atopic dermatitis as well. So when you have those data and try to link their residential address, then we can build up the exposure related to the health outcomes. So that's our birth cohort approach. Then try to look at the 3 main allergic disease. So next one, please. So that's our study population because our school in the middle Taiwan. So I try to look at the middle Taiwan through the southern Taiwan because we have one hospital in Tainan. So that's the reason we try to look at the middle until the southern Taiwan. So we include 630,000 births and follow up until 5 years old for each one. Then finally, we got the 564.869 children in the models. So next one. The first paper we get published in the JACI. We try to look at during pregnancy until after birth. So next one. Sorry, previous one. So when you try to look at the time windows, there are some sensitive time windows between 6 to 22 weeks during gestation. Then after birth, the windows belong 9 to 46. So that's our main findings during pregnancy until the after birth. Then how about the dose response? Next one, please. When you check the prenatal exposure, up to 93, they show the sharply increase the risk. Then after birth, the concentration a little bit lower, only 72, they will increase the risk of the asthma. So that's the dose response between prenatal and postnatal, a little bit totally difference is our second main findings. Then next one. So that's our first paper's conclusions for your consideration. The next one, next one, please. We try to look at the, next one, please. To look at the allergic rhinitis. Then we also have some very interesting finding for exposure time windows. Next one, please. Now, when you try to look at the allergic rhinitis, the phenomena is a little bit different from asthma. Allergic rhinitis, the time window is the day pregnancy until after birth. So that's the allergic rhinitis. Then how about the dose response? The only 26 microgram per cubic meter, they will show increase the risk. So that's the allergic rhinitis findings. So next one. Next one, please. So how about the atopic dermatitis? When you look at the dermatitis, we consider the effect probably is not concentration. They were related to the cumulative. So next one. When we cumulative the PM 0.25, until week 34 during pregnancy, they will increase the risk. After birth, 33. So that's the different phenomena for allergic dermatitis. So when we look at the result, how about the dose? Next one. Next one, please. The dose only 65. So when you look at three main allergic disease, I think the time windows a little bit different. Then the dose response show a little bit different. So that's for our finding can provide some evidence for clinical point of view. They can try to see if their air pollution will influence the development of allergic disease, as well as how about that will influence the medications as well. So that's three papers for us can learn their time windows as well as dose response for PM 2.5 in Taiwan. The next one, how about the components? Next, please. Next, please. When we try to look at the PM 2.5, I think the component, especially for heavy metals, we focus on the lead, ketamine, arsenic, and the mercury. We try to incorporate those components into our models. And I would like to thank our colleague from National Zhongyuan Yuan, Dr. Lin, they try to develop this model for us to look at the PM 2.5 with heavy metals can let us to look at the effects. So next one, when you try to look at the components from PM 2.5, we find very interesting findings. Next one, please. This is, we only look at the Taichung area, as in different components in different places. They show their concentration a little bit different, especially when you have a industry, their heavy metal concentration increase substantially. So that's the spatial variation for PM 2.5 heavy metals distributions. So next one, when we look at the health outcome, I think when you check the lead, there are some effects during pregnancy. Then the other show a little, but a little conflicts. The next one, when you look at the lead concentration, I think only very tiny concentration, 0.026 nanogram, can increase the risk for asthma. So that's our PM2.5 concentration, particular for heavy metals effects. Next one. So when you try to look at the heavy metal in PM2.5, the effect will be during early gestation, then after late gestations. Then I think this would be the further study can focus on the toxicology to look at the effect if really exists in some animal models. So that's our 4 studies. So next one. So our conclusion is when you expose the PM2.5 over 65 microgram per cubic meter, probably you have to pay attention on that, particularly when you would like to go outside for doing some exercise or doing some activities. So I said you have to pay attention on that. Then always the source controlling approach is very crucial. So in the future, when we look at the PM2.5 heavy metals, it mainly from the industry. So controlling for pollutant source, I think is very efficient this way. The next one. So our final conclusion is when you study in Taichung area, I think if we can try to controlling for industrial emissions and use some natural gas to replace our oil power plant generations, I think probably will minimize the risk and decrease exposure substantially. So that's my today's presentation. Thank you very much for your attention.
Okay. Thank you for Professor Huang's very insightful presentation. So because of the time limit, we move to the next speaker. Thank you. So our next speaker will be given by Jialin Zhang from the Kaohsiung Medical University. He is going to give us. When you're ready.
Okay.
Oh, so thank you so much. So when you are ready, please just go ahead. Thank you.
So can you see my slide?
Perfect. Yeah.
Okay, I will start. Hello everyone, my name is Jialin Zhang. I'm from the Research Center for the Precision Environmental Medicine in Kaohsiung Medical University. And today I'm going to share the topic regarding the airborne influenza virus in ambient air. And firstly, I'm going to introduce our research team from the Professor Percy Chen. And our research team was focused on 2 topics. The first one is the infectious bioaerosol, and later we are going to introduce some study from this part. And another topic when we are focused is about the indoor air pollutants and health. We published some paper regarding the effects of air purifier on the indoor air quality and the health outcome among the COPD patient and asthma patient. And another study we focus on the impact of the night markets on the indoor air quality and lung function of the children in nearby household. So we are going to talk about the study regarding the infection bioaerosol, and this is the outline of today's speech. And firstly, the mortality rate of the highly pathogenic avian influenza virus, such as the H7N9 and H5N1 in 2026, was approximately around 40% and 48%. And H9N2 was well known for the acquiring and sharing genetic material between the other flu strains. And interestingly, because the highly mortality rate of the avian influenza virus and the genetic reassortment, so because the genetic reassortment can result in the evolution of the influenza virus and cause the increase the pathogenicity and potentially causing the severe impacts on the both human and poultry. So that's why we want to concern about the outbreaks of the avian influenza virus. And previous study shows that avian influenza virus can transmit through the long-term transmission, such as the dust storm or migratory birds. And Taiwan was located in the downwind of the Asia dust storms. So when the upwinds of the Asia dust storms, such as the Japan and South Korea, have the avian influenza outbreaks. Concurrent outbreaks was observed in Taiwan. And several studies also observed that during the Asia dust storms periods, the cultivable bacteria fungi will increase the concentration during this time. So, but there was no study to investigate the airborne concentration of the virus. And next, migratory birds was also can transmit the avian influenza virus. And because previous study shows that when there was some H5N8 was isolated from the migratory birds in the South Korea, the similar strains was also introduced into other countries through the migratory birds. But there was no study to investigating the airborne avian influenza virus in the ambient air in the winter habitat. So the aim of this study, we want to investigate the concentration of the ambient avian influenza virus during the Asia dust storm days and background days, and we also want to evaluate some association between the environmental parameters and the ambient influenza virus. Additionally, another study will investigate the airborne avian influenza virus in the winter habitats of the migratory birds, and also investigate some important influencing factors, such as the cold air masses and the numbers and the species of migratory birds. So I'm going to show the first study. Ambient influenza virus during the dust storm days and background days. So first, we want to compare two different samplers and choose the suitable for the quantified airborne virus in the ambient airs. So the first one, we use the high volume air sampler, and another one we use the Teflon filter and with the pump at a separating rate of 20 liters per minute. And after we choose the suitable air sampler, the air sample was monitored before 12 hours before the predicted onset of each Asia dust storms period. And the sampling days after the end of each Asia dust storms period were classified as a representative background days. So I'm going to talk about our results and discussion. And firstly, we compare different sampler to choose a suitable sampler for airborne avian influenza virus. And after our analysis, we found that the concentration of the influenza A virus in the filter cassette in the sampler in both spike samples and the unspiked samples was higher than the high-volume sampler. However, the inhibitory rates in the high-volume sampler was much higher than filter cassettes. So this difference maybe depend on the sampling strengths, and if they have a high concentration of the inhibitor, such as airborne bacteria, this may be contribute to the lower sensitivity of this method. So further analysis of the ambient samples, we choose the filters, a Teflon filter within a disposable cassette with a 20 liters per minute sampling rate. And this table shows the concentration of the ambient influenza virus on the Asia dust storms day versus background days, and we found that the ambient avian influenza A virus in the Asia dust storms days was significantly higher than those in background days. And interestingly, we use the backward trajectories of the air masses to observe that these positive samples were detected during the Asia dust storms period was mainly from the mainland China. And additionally, we also evaluated the air quality during on the Asia dust storms day and the background days. And we found that during the Asia dust storms day, ambient PM10, PM2.5, and carbon monoxide were significantly higher than those on background days. So for this study, we found that we successfully conduct a method to quantify the ambient avian influenza virus, and we observed the significant higher concentration of avian influenza A virus observed during the Asia dust storms days and comparing to the background days. And next, we are going to share our second studies, airborne avian influenza virus in ambient air in the winter habitats of migratory birds. And we collect the air samples in the August wetlands, and there were some cases found in the upwind of the August wetlands. And we collect air sample using the Teflon filters with the pump at a sampling rate of 20 liters per minute or 24 hours. And so during the bird migration season, we collected air samples twice every week. And during the background season, from the May to August, we collect air sample every 2 weeks. And this is we use the real-time qPCR for quantify our avian influenza virus in the ambient air. And so I'm going to talk about our result and discussion in this study. And firstly, we found that the positive rates of the ambient influenza A virus was 19%. And the positive rates of the H5, H7, H9 were 8%, 12%, and 10% respectively. And we can show that our study using the air sample had higher positive rate than those compare those used in fecal samples and the water samples. And we also use our data and to investigate the association with the temperature from the Taiwan's Environmental Protection Administration's air monitorings. And we observed that ambient influenza A virus and the subtype H7 and H9 was significantly negatively associated with the daily temperature. And previous study shows that low temperature may increasing the survival of the avian influenza virus. So that may be the reason why we found this significant negative association. And next, we found that the ambient H9 on the days affected by the cold air masses was significantly higher than those on days not affected by the cold air masses. And during our sampling period, there was some human case found in China and the upwind area such as Korea. And from our first study, we also found that avian influenza virus could spread due through the Asia dust storm days. So when the cold air masses come to the south, the numbers of migratory birds increase. That can increase the risk of the transmitting of the avian influenza virus. And also, Taiwan was located in the East Asian-Australia flyway. So further, we investigating the difference between the bird migration season from the September to April and the background season from May to August in the Algool Wetland. And we observed that the positive rates and the concentration of the ambient H7 was significantly higher than in the bird migration season than those in the background season. And previous study shows that white birds can isolate the subtypes of the avian influenza virus, such as the H7. So that may be the reason that we can detect significantly higher of the airborne H7 during this season. And we also evaluate the concentration of the avian influenza virus and the numbers of the birds in the Algool Wetlands. And we found these types of the wild bird, such as answering forms, correcting forms, was significantly positively associated with the airborne H7 and H9. And previous study shows that the answering forms and correcting forms were regarded as the natural reservoir for avian influenza virus. So that may be the reason why when the migratory birds come to the south, that the Algool Wetland can detect the avian influenza virus in the ambient air. We also use this backward trajectory to understand the case form was have from the upwind. Is there have the outbreaks in the upwind or in the downwinds? And we found that if there was 1 week before our sampling date, there have the HPAI outbreaks in the upwind area of the Algool Wetland. The H7 was significantly higher than those during the periods of the non-HPAI outbreaks. It's because the airborne avian influenza virus can detect it in the downwind areas of the case farm in the previous study. And also that the very important thing is that when poultry co-infected with the low pathogenic influenza virus, it can induce to a mutation to the highly pathogenic avian influenza virus and can resulting in the high mortality and morbidity. So that may be the reason why we want to conduct a method and to detect the avian influenza virus in those places such as the winter habitat. So this study is the first study to quantify the airborne avian influenza virus in winter habitats of the migratory birds. And we found some significant influencing factors such as cold air masses and the bird migration season can increase the concentration of the airborne H9 and H7.
Okay.
And also that HPI outbreaks in the upwind area was associated with the airborne H7. So the conclusion of this...
sorry, could we just stop here?
Okay.
Yeah, because it's a little bit late.
Okay.
All right, thank you so much for a very interesting talk. So I will move all the questions to the end because I need to control the schedule. I'm very sorry about that. So we move to the next speaker from National Central University, Professor Yuexia Ruo. Can you bring? Okay. So Professor Ruo, when you're ready, please just go ahead.
Good afternoon, everyone. So I'm delighted to have the opportunity to present our study in this film. So my study focuses on the long-term air pollution exposure and mortality outcome in colorectal cancer patients. Okay, so this is my outline. And the relationship between the air pollution and our health has been studied for decades. So air pollution does not only affect the lung, growing evidence shows that it impacts almost every major organ in the body. So long-term exposure has been linked to shorter life expectancy and higher risk of chronic disease. Okay, so the inhaled PM air pollution can also travel deep down to the airway and enter to the lung, that's triggering the inflammation and causing the shortness of breath, as well as worsen the pre-existing respiratory disease such as asthma and COPD. And some particles can translocate into the circulation and exert harmful effects on multiple organ systems, including alter the gut microbiota and distribute the gut-lung axis. So several sources of environmental pollution lead to the gastrointestinal damage and inflammatory bowel disease and even the colorectal cancer. So study has reported that the pollutant induced the dysbiosis. It means the good guys in the gut decrease and bad guys increase. And then the air pollution also induced the impairment of the intestinal barrier function, and together with the oxidative stress and increase the inflammatory responses and contribute to the development of gastro and intestinal disease. So I summarized several epidemiological studies in the colorectal cancer and air pollution. So this paper published in 2024. So they also utilized a prospective cohort study, the UK Biobank, and then they investigate the association of individual and combined air pollution exposure with the CRC, colorectal cancer incidence and survival. So they found that prolonged exposure to the PM2.5 and nitrous dioxide and NOx is linked to an increased risk of all causes of mortality among the patient with colorectal cancer. And the two evidence from Taiwan. So this paper published in 2021, and they demonstrate that the PM2.5 exposure contribute to both the development of early stage CRC and increase the mortality and potentially acting through the pathway that cause the gastrointestinal bleeding. And additionally, this paper was published in 2025, and the results indicate that the long-term exposure to PM2.5 is positively associated with an increased risk of CRC mortality among both men and women in Taiwan. And however, inconsistent finding across geographic region has been reported. For example, this paper conducted in Hong Kong, they did not identify a significant relationship between the PM2.5 exposure mortality among the colorectal cancer patients. And another paper comparing the United States and Puerto Rico, they found that the nitric dioxide was found to be positively correlated with the mortality from the colorectal cancer, whereas the PM2.5 showed no such association. Okay, so the WHO has released the global air quality guidelines since 1987 to provide the general guidance for decreasing the global air pollution and associated mortality. The WHO updated their air quality guideline in 2021. They recommending a more strict limit on annual PM2.5 exposure, the 5 microgram per cubic meter, due to the additional evidence of the adverse effect of PM2.5 on healthy, especially at low exposure level. So in Taiwan, the air pollution is also an important issue. So this is Taiwan's annual average PM2.5 concentration. So we can see here the 2025, the annual concentration is near 12 microgram per cubic meter, meeting the national air quality target, but remaining above the WHO guidelines. And compared with the concentration in 2024 and 2023, you can see the PM2.5 level in Taiwan show a gradually downward trend. However, all the PM2.5 concentration in northern Taiwan still reach 13 to 50 microgram per cubic meter during the transboundary air pollution event from China. Okay, so we believe that the regional differentiation in air pollution profiling and exposure characteristics likely underline the inconsistent epidemiological finding, highlighting the need for further study to clarify the causal mechanism. So to address this inconsistency, our study investigated the biological effect and clinical association for region-specific PM2.5 exposure using a mechanistic approach. Okay, so this is one of our study. Sorry, wait a minute. Okay, so this study we cooperate with Professor Tang Huang Lin from NCU and 2 experts from NHRI and Lansing International Hospital, and we utilize the animal model and in vitro model to clarify the underlying molecular mechanism of PM2.5 impacts on colorectal cancer. So in this study, we found that the PM2.5 exposure increased the chronic epithelial cell proliferation and colon shortening and gut microbiota dysbiosis, and the gut microbiome changes may be a potential biomarker for PM2.5 exposure impact on the chronic health. PM2.5 induce the autophagy impairment leading to the abnormal proliferation and the P62 accumulation and lysosome damage and inflammatory cytokine ILA releasing. And additionally, we also found that the serum level of ILA was significantly correlated with the regional anthropogenic pollutant. And then in December 2025, we further published a study. So our collaborator, Professor Wang, come from the Kaohsiung Medical University, and then our group we want to investigate examine the association between the air pollutant exposure and all cases of mortality. And we want to identify the high-risk subgroup among the colorectal cancer patients using the detailed clinical data. Okay, so our method, we use the retrospective cohort study, and we included the patient with a pathological confirmed colorectal carcinoma, and each patient AOGS was geocoded to the corresponding village to all the township for accurate matching the estimate the air pollution concentration. So for the air pollutant assessment, the annual average concentration of air pollution was modeled by high precision land use regression technique with machine learning to assess the spectral temperature variability of air pollutant. Okay, so the air pollutants were categorized into 3 levels based on the exposure level. And for pollutant showing significant association with the mortality, exposure was further divided for stage stratified analysis. For example, the PM2.5 was classified with the low and high exposure. So by using this method, the air pollution exposure was systematically categorized and integrated with a clinical stratification to assess the survival differentiation among the colorectal cancer patients. Okay, so this is our patient detailed information, and we enroll almost 5,000 patients with a median survival time of 3 years. So the major result showing here, for the joint effect of the PM2.5, we found the high risk group is stage 4 with high PM2.5 exposure, and we also find a dose response relationship within the same cancer stage. High PM2.5 exposure significantly increase the mortality risk, and even in the early stage cancer patient, they also face an increased risk when exposure to high pollutant level. And for the joint effect of the sour dioxide, SO2, we found the highest risk is a stage 4 patient, and they show the almost 8-fold increased risk regardless of the pollutant exposure level. And notably, the stage 2 with high SO2 exposure demonstrate a higher risk than the stage 3 patient. Okay. So the public health implication of our finding, the first one is the air pollutant as a prognosis factor. We believe that the air pollutant act as a clinical meaningful modifier of the colorectal cancer outcomes, influence the patient survival beyond the traditional staging system. And importantly, the environmental effect is sent to early stage disease and challenging the conventional approaches to risk stratification. And the second two is geographic variation matters. The regional heterogeneity of in air pollutant exposure may contribute to the inconsistent finding across the study. This variable underscore the need for the location-specific risk assessment and tailor the public health intervention rather than one-size-fits-all strategy. And then the protecting the vulnerable population. So population level of air quality standard may provide insufficient protection for vulnerable group, particularly the cancer survivor and the patient undergoing the treatment. So these findings support a target mitigation strategy and personalized exposure reduction effects for high-risk individuals. So for the future research direction, the further progressions requires the integration mechanism study with high-resolution exposure assessment and detailed clinical data. So such approach will enable more refined risk stratification model and inform the evidence-based, the personalized survivorship care. Okay, so that's my last slide. So thank you for your listening. So please feel free to contact me later if you are interested in our study. Thank you.
Yeah, thank you. So thank you for sharing this interesting study. So let's move to the next speaker. Monica Fisharisa from National Physical Laboratory, India. So when you ready, you can bring your slides, Monica.
Yeah.
Okay.
Good afternoon. I'm just going to share my slides. So good afternoon to all of you. And today I'm going to speak about the distribution pattern, seasonal variation, and human respiratory deposition of size segregated aerosols in Delhi, in India. So as all of us know that aerosol is a suspension of tiny solid or liquid particles in the air, and their size ranges from few nanometers to 100 micrometers. And aerosol originate from both natural as well as anthropogenic sources. And natural sources include the sea, salt, volcanic eruption, pollens, etc. While anthropogenic sources include vehicular emissions, industrial emissions, fuel burning, construction, biomass burning, etc. So these aerosols are associated with direct as well as the indirect effects, such as on radiation budget as well as health effects. Health effects include increased cardiovascular diseases, respiratory and allergic diseases, increased mortality. Ultrafine particles can even penetrate the membranes of respiratory tract and get mixed with bloodstream and can cause severe problems. So hence, the study of fine and ultrafine aerosols is really important, especially from health point of view. So for this purpose, we carried out sampling using 8-stage Anderson cascade impactor, which collects size segregated aerosols. And cascade impactor is based on inertial impaction principle, where large particles get deposited on the upper plates, as we can see here, due to their high inertia, while small particles follow the airflow and get deposited on the lower plates. For complete deposition, a backup filter is also used downstream of last stage. And we did sampling for 2 years, that is from January 21 to December 22 on weekly basis. And we collected a total of 79 samples during this whole period of 2 years. Then we collected the samples at CSIR National Physical Laboratory, which is located in central Delhi. This is a institutional area basically. And the samples were collected at the rooftop of CSIR National Physical Laboratory. The site is surrounded by dense forest cover in south, and the agricultural fields of Indian Agricultural Research institute in its west, and commercial and residential complexes in north and east. And site has a very heavy traffic road on one side of it. The site is appropriate for studying the ambient concentrations of air pollutants, as there are no industries nearby the site. Then if we see the average concentrations, average mass concentrations in different size ranges, we see the similar pattern was observed in 2021 and 2022, showing the similar source strength during different months of the year. And the 9 size ranges were then grouped into 3 categories, that is submicron, fine, and coarse. So submicron ranged from 0.43 to 1.1 micrometer, and fine range from 1.1 to 2.1 micrometer, while coarse range from more than 2.1 till 9 micrometer. So as we can see, almost similar variation were observed in all size ranges in both the years, and here when we group them together, the similar situation is there. Then when we see the seasonal variation during both years, submicron and fine concentrations varied significantly, as we can see during winter and post-monsoon. During winter and post-monsoon, while it was relatively stable during summer and monsoon seasons, and the concentration was maximum in winter season, as you can see, and it was lowest in the monsoon season. So what happens during winter season? Low temperature, low wind speed, and high relative humidity conditions, shallow planetary boundary layer, results in the buildup of air pollutants in the atmosphere in Indian conditions. In addition, in winter, wood and coal burning for heating purposes significantly increase submicron and fine particle concentrations. And during post-monsoon season, also what happens, this season coincides with the crop residue burning period in neighboring states. And these emissions are transported to sampling site and higher concentrations are observed. But during summer season, the relative humidity is low, temperature is high, and wind speed is usually high, resulting in high convection activities. Increased planetary boundary layer also facilitate the dispersion of particles, and hence we observe the lower concentrations. And during monsoon, the levels decrease due to the washout of air pollutants through rain. When we did the seasonal log normal mass size distribution of size segregated aerosols, we observed bimodal distribution in submicron and coarse fractions during winter and post-monsoon, while unimodal distribution in coarse fraction during summer and monsoon period. Then to observe the health implication of size segregated aerosols, multiple path particle dosimetry model was applied to estimate the deposition fractions and visualize the deposited mass and deposited mass per unit area of size segregated aerosols in different regions of human respiratory tract. So as we can see, the total, this is the percentage which we inhale or which the human inhale out of total mass. This is the percentage which is inhaled, and then that is again divided into head region and tracheobronchial region and pulmonary region. So as we can see, the total fraction was highest for coarse, followed by fine and submicron in all age groups. But when we see the regional deposition fraction, then fine and submicron fraction had the highest deposition in head and pulmonary region, while lowest in tracheobronchial region. While coarse had the highest deposition in head region, while lowest in pulmonary region. And according to age, submicron deposition was highest in 9 years old. Fine deposition was again highest in 9 years old and 21 year old as well, while coarse deposition was highest in 18 and 21 year olds. Then when we go to the next slide, these are the seasonal deposited mass visualizations for submicron fine coarse fractions in respiratory airways of various age groups in different seasons. Here we see that overall deposited mass was highest in coarse in corresponding to all age groups in all seasons. According to age, submicron and fine had the highest deposition in 21-year-old, while coarse in 9-year-old. So according to the season, submicron and fine fractions, the maximum mass was observed in winter, followed by post-monsoon, and summer, then monsoon, while the coarse fraction deposited maximum mass was observed in summer, followed by post-monsoon, winter, and monsoon. Then these are the seasonal deposited mass per unit area visualizations for submicron, fine, and coarse particles in respiratory airways of various age groups in different seasons. And according to the age, children and infants had higher deposited mass per unit area than adults due to the large surface area to volume ratios. And the vulnerability orders in all size ranges show that 9-year-old are most vulnerable age group. But the limitations of this particular model is that this model relies on simplified idealized airway geometries and symmetric branching, so it cannot fully capture individual anatomical variability in the respiratory tract. And this model is also parameterized for specific age groups only. So deposition estimates for other age groups such as elderly adults for above 50 years cannot be assessed. And since the model structure and default inputs are based on North American physiological and environmental assumptions, it's directly applicable to the populations in that country, and the applicability to the populations in other countries is uncertain. And the ambient concentrations, typical activity patterns, and health profiles can differ substantially between different countries, which may affect inhalation dosimetry and are not explicitly captured in this particular model. So ideally, separate dosimetry models should be developed and validated for different countries for better reflection of local conditions and population age specific characteristics. And here it is the concentrated weighted trajectory plots of submicron, fine, and coarse fractions during different seasons. And here we can easily see that for all the fractions, the sources are mostly local or regional during winter and post-monsoon, while during summer and monsoon, it is local as well as regional, as well as it is the long-range transport of pollutants. So overall, I would like to say that we investigated the influence of this seasonality on mass concentration and deposition fractions of size segregated aerosols in Delhi region, and the submicron and fine particles were more prevalent during post-monsoon and winter seasons, while coarse particles were more pronounced during summer. The log normal mass size distribution displayed bimodal pattern during the winter and post-monsoon, while unimodal in summer and monsoon. And deposition fractions reveal the influence of particle size, with coarse fraction predominantly depositing in head region, while submicron and fine fractions reaching deeper into the lungs. And deposited mass in respiratory airways was maximum for coarse in summer, while for submicron fine in winter in all age groups. And 9-year-old age groups were found to be more vulnerable due to a high deposited mass per unit area. And the concentrated weighted trajectory analysis for various size ranges in different seasons highlighted the influence of local, regional, and long-range transport of pollutants at the receptor site. That's all. Thank you.
Thank you so much. So thank you. So we save 1 minute. So let's move the next speaker. So all the questions will remain in the end. Okay. So let's the next speaker will be giving the talk will be given by Manisha Mishra. So from Azim Pre-Meiji University. So please.
So basically, my topic for today's presentation is disproportionate impact of particulate matter exposure on women's health. So we just saw in this previous presentation which is of course primary study and evidence-based study, where we can clearly see that how these particulate matter actually affecting adolescents and the children especially in their growing age. So here my focus is basically the women's health, and it is more of a concerning kind of topic instead of the primary study. This is more of a review kind of study which I have observed over time. So what happens in India, it is one of the very important and invisible threat. And if you see in India, atmospheric pollutants levels are very high. And 80% of the monitoring stations, if you observe, they have high AQI because of the high PM levels. So what these particulate matter mainly includes basically primary pollutants and secondary pollutants, where we have the primary pollutants from metals or elemental carbon, organic carbon, or different kind of secondary pollutants also get mixed with these kind of pollutants. Specifically, metals are some of the main component which increases the oxidative potential of these particulate matters and causes severe impact on human health. So as you can see that when we see PM10, the larger particles, they mainly affect our upper respiratory system. But as we go from the for the finer particles or ultra fine particles, it goes deep down to the lungs, and also these ultra fine particles get transferred into our cardiovascular system. And how once these particles, which has a lot of different kind of components, they actually interact. Once it goes to our blood system, it causes different kind of impacts on our different organs. For example, there are evidences which have shown that it causes cataracts, it causes neurodevelopment disorder when it gets pumped into the brain system, or it causes cognitive behavior problem, skin aging, respiratory diseases, cardiovascular diseases, which is very prominent in most of the recent studies. And there are latest studies which are also showing that it is causing the premature birth and low birth rate. So when we see PM10, it is mostly emitted from the natural sources like pollens, desert dust, bioaerosols, or sometimes construction dust, which is not so reactive. But when it comes to fine or ultra fine particles, it is mostly emitted from fossil fuels or other kind of anthropogenic sources, including firecrackers, industries. Then there are cigarette smoking as well, biomass cooking. So all these kind of sources cause huge emission of fine and ultra fine particles, which severely affect our especially severely affect the human health. So what happens, the very long-term exposure, if a person has from childhood till the later years, they get severely affected by these particulate matter, and sometimes it leads to death as well. Whereas short-term exposure also causes severe issues like respiratory and cardiovascular diseases. So why I want to focus on the women's health, because we need to, it is the need of the hour because of the rising concern, especially the hospital visits of women and doctors visit related to polycystic ovarian disorders, ovarian dysfunctions, miscarriages, and there are these different kind of problems which is happening among women, and the cases are rising by multifold. So there is a definitely need of attention towards this issue, and despite this like they are affected in the worst form, there are critical gaps because we don't have enough data to support this kind of correlation, or there are not even enough public awareness as well. So if you see, especially in lower income households where people still, especially women in the house, is still using the traditional kind of cooking method, and that causes increased amount of particles, especially in the closed areas. So the major fuels which are used are kerosene, wood, crop waste, cow dung cakes, etc. And when it comes to and women are conventionally involved in the cooking, but there are many outdoor workers as well, which are migrant workers or informal workers who spend long hours outside their houses, and again they get exposed to high level of pollution. So this double burden places women at an elevated risk of long-term, especially reproductive harm. So there are some of the very prominent studies which have been published. One was in 2009 by Grove et al., which have found that there are black carbon particles which has been found in the fetal side of the placenta. So they, especially if you can see this figure here, you can see that the white light which is being reflected, it is because of the black carbon particles which are found within the placenta, especially on the fetal side. Now you can imagine that how these particles going inside the brain of the infants, and how it is going to cause neurodevelopment disorders or the other kind of problems in children. So there are other related studies as well, which has shown that it causes DNA a problem in DNA methylation, and there are other studies as well which shows that high level of pollution causes problem in ovarian reserves. So the air pollution could lead to decrease in follicle, especially follicle antral count, and anti-Mullerian hormonal level, especially exposure to PM2.5 and SO2. And thus, these evidences also suggest that it has a severe negative impact on the ovarian reserve of the women. There is one more study which was conducted on a cohort, especially in China. It was conducted on a cohort of around 91,000 individuals, and it was found that especially women who are exposed in the fourth quartile range of the PM2.5, they have more cases of PCOS and causing around 11 times higher risk to those women, especially because of this higher pollution. So there is urgent need of emissions, especially in India, where the outdoor pollution, not even a single state, if you look at the CPCB websites and get the data, we don't have even single state which is even in annual average, which is even coming close to WHO's guidelines. All are going above WHO's guidelines. So there are urgent need of emission reduction, which is our need of R as well, transitioning to cleaner vehicles and transitioning to cleaner fuel options, also renewable energies, stricter emission control which we need, and there is need also of special public awareness or campaigns regarding the prenatal healthcare system which we need, where women are exposed to excessive amount of PM2.5. We need to take extra care of them, and also in terms of PCOS overall, we need stricter measures to control PM2.5. So this is my final takeaway. Thank you so much. Yeah.
Thank you so much. Yeah. Yeah.
Thank you.
Thank you. So we set for time. Maybe yeah. Anyone have a question for the presentation? Because we save 2 minutes for now.
Yes, I'm ready to answer.
Okay. If not, we can move to the next speaker. Okay. Thank you so much.
Thank you so much.
All right. Our next speaker is Mahesh Pathakati from NRSC ISRO. So please, when you're ready.
Good afternoon, Professor Sheng. Yes, I'm ready. I have shared the PPT. Someone can. Thank you, Professor Sheng. Once again, good afternoon to everyone. Myself, Dr. Mahesh Pathakoti from ISRO, Hyderabad, Indian Space Research Organization. And since morning, we are discussing and we are hearing about how the air pollution impacting environment, climate, as well as health, public health. So it is a kind of anthropogenic disaster, I can say that, because we know the natural disasters such as flash flooding and cloudburst and lightning. But apart from that, if you see in the anthropogenic era, air pollution is also becoming one of the disaster, because according to ICMR report in 2019, it shows that almost 17% of the deaths are happening in the total deaths. 17% are happening from the air pollution in India. So this is a very important, not only regional as well as a global scale. It is very important to understand and track this air pollution continuously, and monitoring and take the mitigation strategies and the informed decision by the policy. So with that objective, we got motivated from that objective. Understand that we have to develop a web-based portal for continuous tracking of this air pollution, and also we are also going to do this integrate the health data to give informed decision about how the air pollution is impacting on health. So with that, so this is a Vayu. Vayu is a geospatial based web-based visualization and analytics platform for air quality as well as the public health over India. So this we have developed very recently. Still, it is in testing stage. So very soon it is going to be operational. So next, please. Yeah. So like as I already discussed, that is our problem statement to understand the air quality monitoring over the Indian region, and also generate the near real-time air quality index and integrate this air quality index with the health monitoring system. And we have developed a portal using the, we are implementing the Open Geospatial Consortium, that is OGC standard, which follows the FAIR policy, that is findable, accessibility, interoperability, and reusability. So you, with that FAIR policy, we are implementing those standards for any users to play with this data and extract the information on board. That is also, analytics is also developed on the web. So some of the the methodology results and discussions will be going into the next subsequent slides. Next, please. So we know the importance of air pollution, and from the morning, from morning session to now, every speaker was talking about its important, and there is a really the need of it developing the understanding the air pollution and its impact on air, human health. So we know the problem. A problem statement is very well understood, that air pollution crisis is as I said, it is an anthropogenic disaster. So for that, now in the recent 2 decades, if we see, it is remote sensing based observations also, the space based observations also strengthening the ground based observations, because ground based observations are involved with the cost, as well as the developing the dense network involves the cost effect. So to have a cost effective solution, so this is replaced by the space based observations, which will have from regional scale to the global scale. So we are using in this particular web platform, we are using the space based observations to develop the air pollution and the air quality index. So in the back end, we are also using the platform Google Earth Engine, and as a service, in the form of service, we are giving AQI, that is air quality index, at a pixel level. So this information, how it is going to be used by the policymakers to give an informed decision. So that we that is what we developed here. Next, please. And when it comes to this in the backend satellite data, it is mostly the Sentinel-5P tropomy and we are using Sentinel-5 Tropomi, also OMI, and also MODIS data. And these are some of the monitoring platforms from NASA. It is coming air quality from space, but it is limited to the few cities. And also the CPCB or CPCB, please, next please. So CPCB, which is a ground-based network over in. So CPCB, we are also known that this is a Central Pollution Control Board over India. This is the nodal agency which monitors the air pollution and gives the informed decision about the air quality over India at different cities. So it is again a ground-based observations. As I said, it involves both costly and as well as the spatial resolution, the limitation of the spatial resolution. But this information is very decisive for city level based air quality monitoring. So this data together with the satellite will complement each other to give a air quality information at pixel level. So that is how we have used the CPCB data as well as satellite data to give the pixel level air quality index. Next, please. In India, how this air pollution monitoring ecosystem works, while meeting the global climate change initiatives are also the national air quality. So, and also like these are the different spheres where the air quality system in India is working, like from different agencies, like National Clean Air Program, which works under Ministry of Environment, Forest and Climate Change, that is MOFCC, who is the nodal agency for India for climate as well as the air quality system. And also IMD's India Meteorological Department, which contributes weather-related information, because any air pollution overlaid with the meteorology will help us to understand its impact on human as well as the environment. So India Meteorological Department is also working on the air pollution research. And Indian Space Research Organization, that is ISRO, is also giving space-based observations for air pollution studies, and where Central Pollution Control Board is playing a major role as a nodal agency for giving this air pollution-related information to the public as well as the policy people. But this, we are following the international standards as well as the regional policies to give this air quality information over Indian region. And this is our methodology. Like here, we developed this portal at a city level, city location. Basically, it is a city level information, and where we give the city boundary, and also we are giving this information at a state boundary, also country as a whole. So it has three options. We can go as a point location, as well as a city level location, and also state boundary and India as a whole. So in that, we are giving air pollution concentration from the space-based observations, which is directly coming from the satellites, that we are giving information through this portal. But on top of it, we are, while following these international standards of computing the air quality index, also the regional air quality index methods, we implemented air quality index using the space-based observations, which is currently under validation, that I'll be showing in the subsequent slides. So here we are giving these two things, like pollution concentration as well as air quality index. The importance of this particular portal is we are able to give this information at a pixel level with the time. So from I mean, one day latency, we are able to give this information to the users. But however, it is currently under testing stage. So this is our methodology. Like we are using in the backend Google Earth Engine, and the critical pollutants such as like carbon monoxide, oxides of nitrogen, ozone, sulfur dioxide, PM 2.5, PM10. So these are the critical pollutants that we are using from the satellite data, and PM 2.5, PM10 we are estimating from the MODIS data. So next please. And this we are all aware of how this AQI is calculated. Like these are air quality index in the table left side, left column. First column is the air quality index for the Indian region, the standards, and whereas the rows, the second column onward, these are the concentrations of PM10, PM 2.5, NO2, SO2, CO, ozone, and these are the ranges. So based on the concentration range, we calculate air quality index. And this is the standard methodology which is adopted in in our study also from the CPCB. And this is how the portal looks like with a buffer of here. A user can give the buffer radius, like 25 kilometer to 50 to 100 kilometer radius from the center, latitude, longitude. So when we give a latitude, longitude of our interest or a city, then it will be able to generate 25 kilometer to 50 kilometer or 100 kilometer radius, the pollution dispersion. We can see the concentration distribution around this latitude, longitude. So, and on the portal itself, we have analytics, like we can see the time series, and also depending on the pollutant, like some pollutants will be applying for the moving average 8 days, some pollutants will be, the moving average window will be 1 month. So depending on the pollutant, so this moving average also is applied to see that how it is with respect to 8-hour window or 1 month window, how this pollution is changing, pollutant is changing over that particular region. So this is available for almost 7 pollutants here, from PM 2.5 to PM 10 and CO03, as I said in the previous slide. So these are all available on the portal. Next. Next, please. And this is the state boundary, like this is Hyderabad city, one of the largest metropolitan city in India. So for Hyderabad, to show that I mean city-wise, how the distribution. So we can understand the importance of having the sub-regional or subscale the distribution of pollutant will tell us that how the pollution is distributed in a given city. So this information will help us to, in the long run, it will help us to see that how the industrial activity is happening and how the industrial activity can be minimized depending on its severity on human as well as the environment. This again air quality index, like we can see that the good air quality index 0 to 50 over the same region, over the same city, Hyderabad. So we can see that satisfactory 51 to 100 AQA. And during the last 1 month average, the AQA, if you see some of the regions like the south and southeast of Hyderabad is showing the high AQA still, but we're not sure still because it is in the development stage. Some of the calculation, especially when it comes to the PM 2.5 estimation, we are doing some more refinement to estimate this air quality index accurately. So which is driven by the PM 2.5. Yeah. So we are using CPCB, that is Central Pollution Control Board data sets, ground-based concentrations to validate with our the concentration of satellite-based concentration. Though it is a surface-based observations which comes from CPCB, that is a pollution board, whereas the satellite gives the tropospheric columnar concentration. But however, in the columnar concentration is also maximum represented by surface. 85 to 90% is represented at the surface, emitted from the surface characteristics or surface activities, whereas the 10 to 15% which comes from due to the convection as well as the advection process. Also here the in the upper atmosphere, transportation also plays a role in the enhanced concentration. But however, when it comes to the direct correlation with the ground-based observation, it will have a 80 to 85% accuracy with the ground data when we compare satellite data with it. And we have done some improvement, because when we use the Sentinel 5P derived AOD product and estimated PM 2.5, our correlation was poor. But when we compared the same AOD from the MODIS satellite, so the MODIS derived AOD shows when we estimated PM 2.5. So the concentration, the correlation was improved almost 80%. So because here the MODIS product which comes at the 550 nanometer is a true representation for the surface reflectance. So this AOD at 550 nanometer is very well correlated with the I mean, from AOD 550 nanometer, we computed the PM10 particulate matter 10. So that particulate matter 10 is compared with the CPCB, which is having 80% correlation between these. Now, because MODIS is again at 1 kilometer by 1 kilometer. So now what we are doing with our own ISRO satellite, that is OceanSat mission, that is OCN3, is also giving AOD product. So now with high resolution, we are going to estimate PM 2.5 or PM 10 from the OCN3 data. Then again, we are going to compare with the CPCB and give this PM 2.5 as a service through our web portal. And again, this is seasonally how PM 10 is correlated, because as we all know that PM10 or any gas will have its own seasonality. It will have seasonal effect also, like diurnal variation, seasonal effect, seasonal variation. So seasonally also we compared, and it has very good correlation. We have done a statistical analysis further on this correlation. So we could see that almost 60 to 70% correlation is observed with the CPCB data, as I mentioned. So the satellite-based observations, always 85 to 90%, it is a representation from the surface emission. So we could also get 60 to 70% correlation between CPCB as well as the MODIS PM10 estimated PM10. So, but this is not still sufficient. So we are trying to further strengthen this validation study to improve better PM10 estimation. Next, please.
You might want to jump to the conclusion or summarize.
Yes, sir.
Okay, thank you.
This mortality study, like many of our speakers also spoke about, and we are also we at this point we are like immature stage. So we are going to do detailed study on this, how the mortality is also getting affected by the air pollution. Next, please. This is one like we have generated in the last 20 years from the emission database, Global Atmosphere Research Database, which is which will tell us the top 10 percentile of the hotspot zones of entire NOx emissions. NOx is not just an environmental parameter; it is also having a proxy for identifying the climate change, because it will tell us the anthropogenic sectors of the carbon dioxide. So it is. The NOx emissions is playing a dual role as for environment as well as the climate change. So this is our future scope. Like as I said, like we are going to implement multi-regression analysis to see that how each pollutant is contributing or impacting the human health. Also, we are going to study that some of the impact on agriculture research, agriculture yield also. And in this portal, we are also going to develop AML-based algorithms to give a near real-time simulations of this air quality index. And thank you so much, and thanks for giving this opportunity. And my special thanks to Professor Umesh Chandra sir, also IP Wing and TSU. Thank you so much.
Thank you. So very nice work. This system could be very useful for this for our community. So let's. Thank you so much.
Thank you. Thank
let's
you,
move to the next speaker, Dr. Naven Kumar Aliwadi.
Yes, sir. Yes, sir.
Time is yours. So please,
yes, sir.
Doctor. Thank you.
Yes, I'm just sharing my slides. Good afternoon to everyone. Yes, I'm Dr. Naveen Kumar Alawadi, Associate Director and Unit Head, BLK Max Hospital. And I am working here since last 1 year. And I am having 19 years of experience in diagnosis and treating a wide range of respiratory, allergy, and sleep disorder conditions. So these are all my area of interest, memberships, and achievements. And we will cover this topic under the following diseases. Like I will cover COPD, what is COPD? I will also cover air pollution, indoor and outdoor. And I will show a study on non-smokers living in urban city of the India and getting COPD later on in their life. So the result of the study is air pollution related increase in COPD cases in non-smokers in urban city of India. So COPD is mainly a disease of smokers previously, but nowadays it's occurring in non-smokers in urban population, and it's called as COPD-P. P stands for pollution related COPD. So what is air pollution? First, I will cover indoor air pollution. Air pollution is the introduction of chemicals, particulate matter, or biological materials that cause harm, discomfort to humans or other living organisms, or damage the natural environment into the atmosphere. So indoor air pollution may be 100 times of the outdoor air pollution, because 90% of the times we stay to indoor, and dirty ventilation system are responsible for 50% of the contributor to the sick building syndrome. And air tightness in the building causes inadequate supply of fresh air. As a result, negative pressure develops, which causes ground level pollutants like carbon monoxide, radon, intro inside the buildings, release of odors, bioaerosols, and other pollutants. So this will cause sick building syndrome. So the symptoms of sick building syndrome are headache, irritation in the eyes, dry cough, itching, difficulty in concentrating, fatigue, and sensitivity to odors. And the solution are remove the source of pollution, increase ventilation, air cleaning, filters, education, and communication. So this is a scenario in the indoor air pollution. You can see a female is smoking as well and cooking inside, and incomplete combustion causes rise in indoor air pollution. So the major indoor air pollutants are carbon monoxide. It's a colorless, odorless gas formed by incomplete burning of carbon-based fuels. And carbon monoxide is 240 to 270 times have higher affinity for hemoglobin as compared to oxygen. So this will causes leftward shift of the oxygen dissociation and rejection of oxygen inside the body causes hypoxia, and that can result in death, even death at night. So sources of carbon monoxide are gas, kerosene, wood, smoke, coal, fireplaces, furnaces, leaking chimney vents, room and water heaters, vehicle exhaust in closed garage, and tobacco smoking. So we can do a sniff air test. We can sniff in indoor, and if we feel like that there are some odor or high level of humidity, or if you are not sensing that the air inside the room is clean, so we can sense with the sniff air test. And how to prevent the carbon monoxide exposure: keep fuel burning appliances in good working condition, never burn charcoal inside, never leave a car running in a closed garage, and consider the carbon monoxide detectors. So indoor air quality we measure with the help of indoor air quality index, and to get rid of this indoor air pollution, we can do natural ventilation as well as artificial ventilation. So ventilation is must if we want to prevent the indoor air pollution. Now we talk about outdoor air pollution. Indoor pollution is of two types: natural pollen grains, fungi, mineral dust, and anthropogenic sulfur dioxide, nitrogen dioxide, carbon monoxide, PM 2.5, PM 10, and lead. There is another classification of air pollution: primary pollutants like sulfur dioxide, nitrogen dioxide, metals, and carbon monoxide, and secondary air pollutant is ozone. And this is the air quality index. 0 to 50 is good, and 51 to 100 is moderately polluted, 100 to 200 unhealthful, 200, 300 very unhealthful, and more than 300 is hazardous. So what is COPD? COPD is a progressive lung disease like emphysema and chronic bronchitis. So it is caused by cigarette smoke and air pollution mainly, and leading to damage of the air spaces and the lung parenchyma, leads to chronic cough, shortness of breath, and wheezing. And while there is no cure, only the management focuses on the avoiding the triggers, using medications, and pulmonary rehabilitation to improve the symptoms and quality of life. So there is no cure of COPD. Once the patient develops COPD, there is no cure. Only the thing we can control is symptoms, and we can improve the quality of life. So nowadays COPD occurs in urban population due to high level of air pollution, especially in non-smoker, and this is called as COPD-P. And due to smoking, it's called as COPD-C. So there is a difference between COPD-P and COPD-C. COPD-P is mainly due to pollution, and COPD-C is mainly due to cigarette smoking. So main types of COPD are chronic bronchitis, long-term cough with mucus, and emphysema. The key characteristics are symptom develop slowly but worsen over time. So this is a healthy airway, and you can see the healthy lung, and over the right side you can see the COPD airway and the destroyed lung parenchyma in COPD. So common symptoms, we all know: wheezing, chest tightness, fatigue, cough. Diagnosis mainly on the history, X-ray, CT scan, and pulmonary function testing. And causes and risks are the long-term exposure to lung irritants like smoking, air pollution, and there are some genetic factors as well. So in our study, we have done a study on 4 patients living in New Delhi. All are non-smokers and not having any other comorbidity. So in our study, we have done bronchoscopy on 4 patients and have noted the presence or absence of anthracotic patches inside the bronchial mucosa. So we have also keep on recording the follow-up history, clinical examination, and PFT of all patients. So study results, anthracotic patches seen in the following patients during the bronchoscopy. So all patients are residents of Delhi and never smokers. So patient number 1 is Sumit Kumar, 41-year male, having small anthracotic patches in the right middle lobe. Patient Satyavati, 76-year female, resident of Delhi, never smoker, having multiple anthracotic patches, bilateral lung fields. Bal Kishan, 67-year male, multiple anthracotic patches in bilateral lung fields, never smoker, resident of Delhi. And fourth patient is Maliram, 83-year male, having anthracotic patches at the carina and left upper lobe. So these patients were found to have obstructive pattern on pulmonary function testing, and history and clinical findings also suggestive of obstructive lung disease. So in discussion in our study, it has been clearly shown that living in urban city of India like New Delhi can cause occurrence of anthracotic patches, black color patches inside the lung bronchial mucosa, and the development of anthracotic patches due to pollution in non-smokers are independent risk factor for the development of obstructive lung disease in future. So these are the some slides showing black pigmentation inside the airway. This is the right upper lobe, picture of right upper lobe showing anthracotic patches. This is the picture of carina showing narrowing of the left main bronchus and patches over the carina. In this, we have found that patches in right lower lobe, and in this we have found that there is tar-like deposition of the material inside the right lower lobe, and we have removed this carbon-like deposition through the airways of the lung. And I'm having one video of it. I can show you in the next slide. So I'm just playing the video. So this is the picture of the bronchial mucosa we have seen with the help of bronchoscopy. So you can see this is a black color material inside the right lower lobe and multiple anthracotic patches in bilateral lung fields. And this is the removal of this tar-like material. And this patient eventually developed severe COPD. And in follow-up visits, we have done pulmonary function testing, showed the gradual deterioration of FEV1 in spirometry, as well as patient developed breathing difficulty, MMRC grade 4, eventually later on. So this is the material which we have removed. Patient having persistent cough, breathing difficulty. So during bronchoscopy, we have seen this material and we have removed. Patient partially relieved in his symptoms, but eventually he got severe COPD, and he was non-smokers living in Delhi. Okay.
So you have 2 minutes to finish.
Yes.
Okay, thank you.
Okay, thank you. I have just finished my presentation. If anyone have any question, I will try to answer.
You want to stop right here?
Yes.
Carlo, I just want to ask one question to Dr. Naveen.
Yes, sir.
Okay.
This data what you showed that all 4 patients they were found COPD E.
Yes, COPD P is CO2 pollution. Yes, COPD P. COPD A is asthma related. COPD is known as COPD.
And P pollution. So you found pollution.
Pollution. Yes. P is pollution. C is cigarette smoking, and D is developmental and genetic.
I just want to clarify. You are practicing in Delhi for a long time, and this year it was so much, several doctors, they suggested leave Delhi. So do you have some kind of data or to say to this aerosol community that this the number of patients respiratory problem that is increasing, or COPD P type people are increasing, that with what confidence, something, can you share that?
This study is currently going on, so few more patients I will add on in my later lectures, and if I will get the physically to present my study, till that time I will complete this study. So half of the study has been done. So there is clearly the increase in the number of COPD-P. So previously we were having only 9 out of 10 patients having smoking related COPD, only 1 patients are having pollution related COPD. But now the proportion is almost around 6 is to 4 patients. 6 patients are smoking related and 4 patients are pollution related. So nowadays COPD is occurring in younger population as well. Younger population and non-smokers getting COPD, the numbers are increasing. And the detailed results of this study, I will add on few patients more in the later coming months.
Another question is linked to this. Any kind of tracers which are linked to chemical analysis or that do you use other than your clinical expertise?
No,
For
sir.
example, if this is related to pollution, then some heavy metal analysis, do you do that in viscera sort of thing, that mucus?
We have taken an occupational history, and occupation wise there is no occupational hazard which is causing COPD to those patients. All are having office work in their life, and there was no other comorbidity.
Very interesting. Thank you very much. Very important work.
Thank you. Thank you very much. This is very important. Thank you for sharing this very important information to everybody here. So let's move to the last speaker. I heard about Alok Chopra. He is in emergency outside of the town. So Umesh, who going to present this? The last speaker?
Dr. Alok Chopra, who is a cardiologist, very famous in Delhi, and he also had some lot of work he has shown on Instagram. People he has millions of followers. He committed to share his research, but he got some emergency to attend that out of Delhi today. So he has sent his presentation. I have shared that presentation to Moki. Moki can share, and we can all have that benefit of his experience. Dr. Alok Chopra. Moki, can you share Dr. Alok Chopra presentation? And that is AI based. So I think that is something differently prepared.
Okay.
This is somewhere you have to click, then it comes. Can you make it bigger? So if you click somewhere, or you can read. You can read this each and every slide, but there is somewhere you click, multimedia comes and photo to another. So can you make it like that, bigger size, or can you read it? I can't read that. Yeah. So this way we can read it. That even I can read that if you permit.
Kind of give a story.
Yeah, he has given, but that was this is coming like that, but that is multimedia assisted basically. We can read that. We say that I am ashamed of what my city has become. I am Dr. Alok Chopra. Delhi is not just my birthplace, it is my home. It's where I grew up, where my children grew up, where every memory of mine lives. And yet today, we are breathing some of the most toxic air on the planet. This didn't happen suddenly. This has been our reality for almost a decade. Back in 2017, many of us doctors marched at India Gate. We warned that this crisis was coming. Well, it came, it stayed, and now it shaped the way we live every single day. What troubles me most is how normal everyone has made it. People have stopped wearing masks. Children still go to school, no hazard test. We look around and think, if nobody else is doing anything, why should I? Let me say this clearly. This is not normal, and it should never be treated like it is. Next. Next. I think you have to. Next page or below that page. And go forward, Moki.
Yeah, this is the next part.
Somewhere the vitamin and something. Yeah, this one. As a doctor here is what I would advise you must do right now to protect yourself during this severe air pollution. Number one, basics, wear N95 mask, keep children and elderly indoor as much as possible. Run your air purifier, especially at night. Avoid outdoor exercises and stay well hydrated. Number two, use targeted supplement to fight inflammation and oxidative stress. Essential combinations: vitamin C plus vitamin E, powerful oxidant. Curcumin reduces inflammation, and quercetin reduces oxidative stress. Beta carotene protects from cellular damage, and sulforaphane from that comes from broccoli sprouts boost detoxification pathway. This is something he shared while going out. So this is some. Thank you very much for just for your patience. Now you can proceed further, Carlo, for this session.
Thank you for reading this notes for us. It is very important for, even I don't know how to protect except to the mask. So
there are other clues he has given, but we can say
advisory from doctor is very important. So maybe you can share this article to everyone after the world. Okay. Thank you. We finish all of the presentation in the session 2. So it's very success, and I think everybody done very well on the presentation, and with a very insightful knowledge, of presentation. So I think that you maybe have some questions. Anyone want to ask questions? It's time for questions.
Let me see. Let me check whether I would like to have someone to say something about it. I mean, 那个黄炳芳院长在吗？
在。
Yeah. So would you like to make some remark first? I mean, your first time to come to such a forum. I mean, and sharing. We heard about this, and in fact, the last time last year in the forum, on the online forum, we did not have that much discussion on the health issue, right? And then this time we have a lot, so it's really in your alley. And so I would like you to make some comment, see how the purpose of this forum is to promote cooperation of Taiwan with the neighboring countries. So I think you're in a very good position to have the overview on the situation.
Sorry, I cannot hear. Can you repeat your question? Because voice a little bit.
Yeah, I was saying that that the forum meeting here is to promote cooperation between Taiwan and other neighboring countries on the air pollution and public health. And your university has been doing a lot on this. So I think I would like to hear your impression.
Okay, thanks a lot.
And what you want to do, I mean, say, suppose you think that this is a good thing to do, and how we could help or how you could help.
Probably for this forum, we can do it the similar way in both sides, because I think the air pollution in India probably is higher than Taiwan, but the satellite thing is free of charge. So we can try to develop some similar way to collaborate in the future, especially for PM 2.5 for ozone, for sulfur dioxide, and so forth. So far, I think both sides probably I will propose probably related to the SIM, the satellite base. Probably is the one thing we can do some exposure assessment in the similar way in both sides. The second, probably the health outcome, I think a lot of physicians, if you are interested, probably we can look to their clinical data. So we also have some data, not just for health insurance, but also have the hospital base. So I checked today's lectures, a lot of physicians using their own data. I think it's a very good way to look at the biological mechanism further. So that's two things I had for this forum. Okay.
Okay, thank you, Professor Fang. Professor Tang Wang 林老师也在吗？
他不在这边
我在。
Sorry.
Okay. Do you want to comment? Because I'm looking really forward to your satellite program, that whether you could help Nepal, Bangladesh, and Pakistan, and of course New Delhi. Delhi.
Yes, I think there are a lot of the satellite project under proposing. So you can see in the near future, there are a lot of satellite observation can be applied, and the more spatial as well as temporal information, especially focus on the environmental exposure can be provided in near real time. So in my perspective is that the early warning for reducing the impact of air pollution on human health is very important. But before this, actually, we need the kind of the disease or risk or mortality impact from the public health or from the doctors, such as the Dim Fang, just provide us how the component of PM 2.5 affect the human health or human disease. So I think for the environmental exposure can be expected more detailed information in the near future. But we still need the the risk assessment, especially for the early warming for the disease. That's my short comment or opinion for this forum. Thank you.
Yeah. I think that the last 2 or 3 talks by the two, I think who was that? Mahesh, are you there?
Mahesh.
You want to say something after regional orders? I cannot hear you. Well, I mean that the mic is open, but then we cannot hear the sound. Any other one want to make some comment? We still have some time. Dr. Dr. Alavadi, you gave very interesting, kind of clinical talk.
Yes, sir.
And
Yes, sir. Yes, sir.
yeah, you have to. I mean, the first time you meet, you're meeting Professor Bingfang Huang. He's the dean of the medical college, so I think that would be. I think you two have something very lot in common. Maybe next time you two could discuss more, exchange information, because he has a lot of data in his hospital, and I think the same with you too. Yeah.
Yes, sir.
Maybe that I could, if you like, I could from Marky's email address, email to you, messages to you. You can find his email anyway. If you like, you could write to him. Yeah.
Yes, sir. Yes, sir.
Yeah.
You can text me on my mail. Yes, sir.
I'm not sure that Mr. Huang want to travel to Delhi, though. From what you described, it's so dangerous.
Yes, sir.
Carol, you want to say something?
Oh, yeah. Thank you for giving the opportunity to chair this session. I learned a lot, especially Manish and some Professor Huang also point out the fine resolution of PM 2.5 data is very useful for health assessment. So from satellite can create a very fine resolution with the machine learning method. So the Mahesh, you have a very good website to demonstrate the PM 2.5 spatial and the time distribution. So will you be interested to working with Taiwanese colleagues, maybe from our aspect to integrate those data set for different regions? That could be very interesting. And yeah, so that's what I'm thinking for technical. This kind of a technical tool is very useful for follow up and can make the program more successful in the future.
Sure, Professor Sheng. We will.
I think we can ask Kundan something. Kundan, are you?
Yeah, I'm here. Yeah.
Please, if you want to say something for further future or what future planning.
Yeah. So because basically I'm a modeler, so I can contribute through my modeling expertise. Yeah. So this looks quite exciting. So many things came up, right? So this you could say data visualization platform as well. Just now we're talking, right? So there also how to integrate the model data or generate the model simulation results. So I'll be very, you could say, willing to contribute to this kind of work. Yeah. Yeah. Thank you, sir.
And you're from Nepal too, right?
Yeah, I'm from Nepal.
Yeah, it's quite interesting and amazing. You know, you're doing such a good job. Right.
Thank you. Thank you.
I think Mahesh is available. Mahesh is now available.
Sir, are you able to hear me, sir?
Yes, yes.
Yes.
Yeah,
Thank
want
you,
to
sir.
say something? I mean, I asked you to say something.
Yeah, I mean, once again, thanks to Professor Umesh sir and Professor IP Wing and also TSU, Taiwan Space Unit, for the opportunity. As Professor Sheng said, the integration of AML-based generation of PM 2.5 high resolution product and integrating that product with health parameters, maybe we can taken up on a serious note, because as everyone, like all experts are sitting here, everyone knows that PM 2.5 how it is adversely affecting on human health. So maybe that collaboration we can do it in the future, near future. So we are ready to work on that. So that's what I want to convey.
Yep. Thank you.
And Arjit.
那个罗月霞老师你在吗？不是罗，月霞罗。
Arjit, you want to say something? Arjit is not there. Huh?
那个张嘉玲在吗？
I'm here. I'm here.
Yeah, want to say something? You're the youngest. You so you I can force you to say something. And turn on your camera so everybody could see you.
Okay. Hi.
Yeah, she's still a master degree student, right? Am I right? Yeah. Yeah, working for her professor. Her professor is Jovering. All right. So, what's your impression? You want to do your PhD after listening to all this interesting talks?
I think the air pollutant may lead to the adverse health effect. And my study in my PhD program is focused on the effects of the air purifier intervention on the indoor air quality and the health outcomes among the asthma patient and the COPD patient. And we found that after our intervention, because our study area was focused in the industrial area in Kaohsiung City, the Shaogang district, and which is the heavy industrial area. And I think that the resident in this place was suffer from the severe air pollutant issues. So when we cannot improve outdoor air pollutant immediately, so we just want to use the air purifier in their home and to find whether if their health outcome and improve. And we just do the short-term intervention, and we found that there was have improvement in the lung function in the asthma patients. But it's really difficult to find the significant, just find some marginal improvement. And our air purifier for our mechanism of our air purifier, we focus on the photocatalytic oxidation, which can remove some gaseous pollutant, such as the sulfur dioxide and volatile organic compounds and the carbon monoxide. And I think this gaseous pollutant was more sensitive to this patient. So I think if we cannot just improve outdoor air pollution immediately using the air purifier in the household is maybe a useful way to improve their air quality and their health. Thank you.
Yeah.
Very good. I think, Prasenjit, do you want to say some last words of this meeting?
Actually, I want you to tell us about the September meeting, because that would be the next major event, right? The next September meeting in Delhi. Either you and Carol could tell us something more.
Umesh, you want to say something about the meeting? Or no?
Yeah, already I briefed that meeting that will be from September 7 to 11 in Delhi. Basically, we were planning to hold this in JNU. But yesterday, we had a discussions with TECC. They also want to support little more money there. So the venue, we can have a hotel where most of the participants will be staying, and there won't be any problem moving from here to there, transport issue. So and also the facilities are better from that angle. We are planning now to organize this in a hotel. Nearby hotel, JP hotel is there.
Can you tell us what that meeting is about?
Pardon?
I mean, what's the purpose of that meeting?
Voice is breaking. I'm not able to hear.
I mean, what do you want to do with the meeting?
Yeah, in that meeting, we are inviting basically resource persons and participants. That meeting is on air pollution transport. As I highlighted, transboundary pollution and long-range transport are basic issue in terms of air pollution science. Other than it's medical aspect, but from science point of view. So this is more about air pollution, transport, and acid deposition, with the chemistry and transport basically. So those who are expert in chemistry and transport, they will be resource persons, and those people who are young people working in university and institutes, they will be called for some kind of training. And also there will be regular lectures. We have not yet finalized, but there may be some exercises given to them to calculate, to estimate, to run some model kind of thing. And so this will be the beginning to fractionate, import export, what I was talking about, based on LRTP sort of thing, which Carlo has also given some input as estimate how much it's coming. You can fractionate that one, and at the same time that approach given by published by Professor T.H. Lin and also Carlo Group, that BC dust, that kind of separation, and then you correlate that with air quality, not with directly PM 2.5, which is not much of informative, because sometimes natural input is there in that one. So if you have fractionated or basically chemically speciated PM 2.5 correlation extracted out of AOD values, that is really going to help. Even the Dr. Naveen, what he projected, that clinical is seeing in lungs that COPD P that can be correlated because further some people we will encourage to do chemical analysis in terms of metals of aerosol, and those metal we will take help of doctors to see that in the basically organ how much it is. So the correlation of that I'll probably some receptor model type thing will help to estimate really it is happening or not happening, because this is one side of doctor, but other side of scientists, when you club that chemical analysis and that chemical analysis, then radiological tests and physical, all type of this tests what Dr. Naveen mentioned, then really we will be able to. Right now, physically it is seen that air pollution is a problem. People are saying, doctors are saying, but scientists or any policy require data, very solid data basically. So number of patient here is a 4. So if there are different country, Pakistan, India, if we select some this kind of doctor group, and then chemical analysis of aerosol and that part. So this is one outcome we can think of out of this meeting, that further we can have a team. That is one aspect. Only air pollution and clinical trial is another. Is air pollution, chemistry and transport, that is other aspect I'm talking, because there are different groups working on that. So this is going to highlight, and also we are going to have a network, because it is not possible to include all people working in India. India is so huge. The number of working in particular domain is so huge. So we will select some people, but some people, those who are not even selected, working with government, we have to see how to connect with them so that it can be conveyed for a better policy, effective policy management. Because without conveying to government, any government, whether Indian or Nepali, they require connection. So from that angle, we have to see how which channel or who is the representative who can get connected with that to really communicate our research to policy. So this is other aspect. What I want to even highlight here, other than the meeting, out of this meeting, we have 3 major outcome we can see. One, as I mentioned, as Professor Lin T.H. mentioned, that project, a specified project. By selecting some of the expert, we can submit some project to some agency. That one thing. Another is we can plan some campaign, field campaign like Indian Ocean Experiment, and that campaign can be very useful to understand chemistry and transport in that one. And also we can have collaborative research. Select individual group in India and Taiwan, Nepal, Taiwan, like that, so that it can have both way benefit. So this is another third aspect of how we can go further. And then I have a certain other thing which we should see in aerosol and air pollution thing. That is, we have to decide. Somebody is doing PM10, PM2.5, PM1. What we cannot have all type of. We have to select which is more crucial for health. For example, 2.5, and now many people have samplers. So 2.5 we consider, and accordingly we do chemistry. Now, what chemistry we have to define parameter. Many people are doing VC. Some people anion cation, some matter. So we have to select some and encourage this whole community what we have. So please concentrate and publish your work based on these, and then that will be taken up for further clinical trial correlations or that kind of thing. So we have to select that. Then correlate those values with AODs. That is more important. That how to correlate air satellite data, remote sensing data, and using this, because one of the objectives we have highlighted, ground-based data and remote sensing data both are important, and from that angle we have to focus on how to club that. So we have to make a team working on this aspect, chemical speciation, then AOD data and ground-based data, and some people, young people, should be involved in that. And now there are so much to do with AI. Miracle can be done by using young people and AI together. So this is one aspect. And then what I see, there is a good scope of doctor to doctor of India and doctor of Taiwan collaboration, that already Professor Ip mentioned to Dr. Naveen, that kind of collaboration, because this is because exchange of knowledge, and at the same time the exchange of medical expertise, not only pollution. So this is also required because what we are talking is only one dimension scientist, but here it's a other way also. This can help, and it can have better relations between two countries. Now coming to further to that meeting, the meeting will be for 5 days. 1 day for workshop, one day for field trip, and rest of the days we will have kind of brainstorming meeting, lecture, and that as usual what happens. And we will invite very select people all over the globe, or mostly focusing on Indo-Pacific region. And the region, as I mentioned, major countries, even they don't have expert in that particular in this field. India is having plenty of that, but when we search around, very few people are working. So first that we want to trigger some kind of sensitize to small nearby countries like Cambodia, Laos, I told Myanmar, where air pollution experts are not working really. They are taking help from outside. So we want to build capacity in those and have our own network. And that once we have these ground-based satellite nearby in small countries, then we can link that satellite data very well, because otherwise there will be a huge gap if the network is not complete. So this is another objective of that meeting. What else? And overall, the meeting will be guided by Professor, if this is the best point of that. So we don't worry to what further can be included.
Okay, good. So time's up. Let's have thank you very much, Umesh. I think you're going to write it down, right? And then send it us. And everybody will be welcome to that meeting in September. But the last thing to do is that, can you turn on your camera to have a group meeting, to have group photo?
Yeah, please. Switch on your camera, please.
Yeah, and Shrestha, you're not
Kundan. Dr. Naveen, please switch on your camera. Mahesh, those you are.
I'm going back.
Yes, sir.
Yeah, please switch on your camera.
Mahesh,
Yes, sir. Yes, sir.
Mahesh, and everybody, please.
Yes, sir.
Okay.
Yes, sir.
I mean, this video will be shown, but the link will be sent to you, so you could look at, go back and look at what people have said and what you have said too. Yeah.
Yes,
and,
sir.
I'm sure that Umesh is going to write a report, on summarize the outcome of this meeting. And thank you very much. And because 2 days from now will be the Lunar New Year, and Happy New Year to everybody. Yeah. And have a good time. Yeah. Bye-bye.
Okay.
Thank you. Thank you.
Bye-bye.
Bye-bye.
Nice. We will be working with
Yeah.
Thank you. Let me thank